Hello and welcome. My name is John Horvath. This presentation is about deep foundation design and the changes that I feel need to be made in the way that we go about doing this. Well, as this slide indicates, this is part 2 of the presentation. As I indicated at the beginning of part 1, in order to satisfy YouTube requirements, I've had to break this presentation into 2 parts. So for those of you who have already viewed part 1 and are continuing on to part 2, again, thank you for your time and effort to view part 1. Please sit back and enjoy part 2. For those of you who are starting here at part 2, I would strongly recommend that you close the presentation at this point and go back and watch part 1 first. You really will not understand what I'm doing in part 2 unless you have viewed part 1. These are the 5 modules that I've already covered in part 1. The 3 remaining modules I have highlighted here will constitute part 2 of this presentation. Let's begin by moving on to what I call a change in thinking phase 2, where I show you how easy it is to design deep foundation elements for axial load based on the serviceability limit state and settlement. And as with the phase 1 module, there's quite a few topics that I want to discuss, so I have broken this up into a number of segments and subsegments. And let me begin with a prologue to kind of set the stage as to what this phase 2 presentation module is all about and how it came to be. Well, as I stated at the outset of this presentation, the primary goal of this presentation is to promote change, to move past the centuries-old meme of designing deep foundation elements for axial load based primarily on the geotechnical ultimate limit state or failure, and advance the thesis that the geotechnical serviceability state displacements should always be the priority in deep foundation element design, with of course due consideration of the structural ultimate limit state. The goal of this phase 2 module is to show how this change can be implemented in a way that is reasonable to use in routine practice. It's very important, yet sufficiently robust in its theoretical basis to use in academic research, which is also important. Furthermore, it will be shown how this change can be implemented immediately, not at some ill-defined time in the future, simply by using presently available knowledge that has been, if you will, hiding in plain sight for literally decades. So before moving on to discuss how all of this can be accomplished, it is necessary to address and dispense with some issues that have been brought up over the years and are a distraction to the present discussion. And these are issues with which I have had personal knowledge and experience. If we ignore the simplistic piles don't settle mindset of some design professionals, and not to beat up on architects, but in my experience, this is largely the professional sector where this comes from. I've lost track of how many times when I was in design practice full-time in the earlier years of my professional career that I would be involved in some project and an architect would say, footings settle, piles don't settle, my building is precious. Every architect's building is precious. My building is precious, it can't settle, I want to use piles. Piles don't settle. So that was the common argument I would always hear. So if we ignore that, and that certainly persisted well into the 20th century and probably still does to the present to some extent. An argument is sometimes made that there is already consideration, albeit indirect, of the geotechnical serviceability limit state in the current design state of practice that is based on the geotechnical ultimate limit state. So we don't need to consider the geotechnical serviceability limit state explicitly. Now, the basis of this argument is that the Davison offset limit criterion for defining the geotechnical ultimate limit state that is used almost universally in the United States implies that geotechnical failure, quote unquote, of a single deep foundation element in a static load test occurs at a relatively small magnitude of settlement. As you know, the Davison offset criterion is basically the elastic compression of the deep foundation element shaft plus a small, I mean by small we're talking about a few millimeters, fraction of an inch increment. So consequently, when you apply a safety margin to the geotechnical failure load determined using the Davison offset limit criterion, the implied settlement under service loads is even smaller magnitude to the point of being negligible. So people will argue, well, you know, indirectly we already consider settlement. Settlement's going to be almost negligible, so we don't need to discuss it further. Well, as I think I've shown you already, and as I will show you further in this presentation module, this logic is flawed as it does not ensure that deep foundation element settlements will be small in all cases, especially when group behavior is considered and or there are post-installation global settlements. And certainly that is not the case nowadays with with energy piles. Consequently, the current design state of practice that is based on the geotechnical ultimate limit state should not be considered as already adequately addressing settlement in the geotechnical serviceability limit state, which means that we have to develop a design methodology that explicitly addresses the geotechnical serviceability limit state if we want to advance the design state of practice. If we want to get out of this 200-year-old meme of the way we've been doing things. Well, I now want to discuss some background information as to why I selected things that I did for this Phase 2 module. Now, as I've noted throughout this presentation, both the design state of practice as well as academic research for deep foundations subjected to axial loading have been fixated on the geotechnical ultimate limit state for almost 2 centuries now. Nevertheless, there's been a surprisingly large knowledge base dealing with the geotechnical serviceability behavior of deep foundation elements subjected to axial loading. And this has been developed beginning in the latter decades of the 20th century and continuing to the present. And this is due really to the persistent research and publication for a relatively small cadre of researchers who have remained focused on the goal of promoting greater awareness and use of settlement, the geotechnical serviceability limit state, in both practice and research. Now, in addition, during the same time frame, there have been, I think, tectonic advances in computer-based computational tools, as well as site characterization based on in situ testing tools, especially the cone penetrometer in its current piezocone and seismic piezocone variants. And I've been in practice long enough, over 50 years, to have personally gone through this transition. Certainly when I was an undergraduate and early in my professional career, a slide rule or later a pocket calculator, pencil and paper, those were your primary tools. So I've lived firsthand the tremendous advances that have occurred in the last several decades. Well, the net result of all this is it turns out that the design state of practice for deep foundation elements subjected to axial loads can actually be readily migrated to focusing on serviceability and settlements instead of the ultimate limit state, simply by drawing on underutilized existing technical knowledge that, as I said, has been hiding in plain sight now for decades, and revisiting this technology using modern site characterization and computational tools, as well as just some clever combination of this knowledge. So, that having been said, there needs to be judicious selectivity when drawing from this existing knowledge base of deep foundation engineering element, geotechnical serviceability behavior. This is because a stiffness and displacement based analytical methodology and any specific analytical method derived from it that is developed for use in design practice needs to consider all the relevant aspects of soil structure interaction between a deep foundation element and the surrounding ground, such as residual loads from installation, post-installation global settlements, and in the case nowadays of energy piles, the thermomechanical behavior. In addition, any new stiffness and displacement based analytical methodology and resulting method needs to be compatible with modern site characterization and computational tools. Most importantly, any new stiffness and displacement based analytical methodology and resulting method needs to be amenable for use in routine practice. Otherwise, it will languish indefinitely as an academic curiosity. So the point I'm getting at here is there's a lot of stuff that is out there, but we have to use it judiciously. And we always have to keep in mind that we want to develop something that is practical for use, both by design professionals as well as by academicians. As I noted earlier in this presentation a couple times, I've seen many really interesting, clever solutions developed in academia that have gone nowhere in practice because of their complexity, or you have to buy some one person's special computer program in order to make it work. Now, historically and to a considerable extent to the present, the focus of R&D into the geotechnical serviceability limit state for deep foundation elements has been on analytical methodologies and methods for the low displacement behavior of a single deep foundation element as the result of post-installation load application at the head of the deep foundation element. And this is understandable, and it certainly is a reasonable starting point in a baseline case, given the fact that deep foundation elements are indeed installed and load tested individually. So there has always been a desire to, if you develop a new analytical model, you want to see how it replicates a static load test. And you do this as a way to verify and calibrate any new model that you develop. So although we use deep foundation elements in groups or clusters in most cases, certainly in terrestrial applications, using the individual deep foundation element, single deep foundation element as a baseline case is certainly very reasonable, because as a minimum you have to make sure that you could replicate the behavior of a static load test before you now want to extrapolate this to group behavior. However, because especially in terrestrial applications we do use deep foundation elements in groups, we do need to consider group behavior. And this is because group behavior can differ both geotechnically and structurally from that of a single deep foundation element. And this is another area where the current state of practice that fixates on the geotechnical ultimate limit state, you run a static load test, you apply your Davison criterion, or if you're in Europe, you use your 10% settlement criterion, you come up with an allowable value, and then you assume that even though you're going to use these deep foundation elements in groups, that this extrapolates to group behavior. And that's not necessarily a given. So it's clear that a design state of practice based on a combination of geotechnical serviceability and the structural ultimate limit state has to consider group effects where relevant, in addition to the baseline behavior of a single deep foundation element. So again, it's fine to start with a model for the single deep foundation element, but you then need to be able to scale up those results to group behavior where necessary. It's also clear that a design state of practice based on geotechnical serviceability and the structural ultimate limit state needs to include behavioral phenomena that have historically either been ignored or treated incorrectly. And this, of course, includes residual loads from installation and the effects of post-installation global settlement. Obviously, your Davison offset limit criterion applied to a static load test or your 10% settlement criterion applied to a static load test is not dealing with residual loads and is certainly not dealing with post-installation global settlement. And finally, it's clear that a design state of practice needs to be able to accommodate new technology such as energy piles that are part of a ground-sourced heat pump system and are subjected to thermomechanical behavior. So I'm simply saying that the current state of practice based on geotechnical ultimate limit state really fails us in multiple ways. We need to be able to consider all the different sources of settlement and load for deep foundation elements that I talked about in the preceding module. And we also, for designing energy piles, we also need to consider the thermomechanical behavior that I talked about in the preceding module. So in summary, the challenge in developing a rational methodology for a deep foundation element design state of practice that is based on geotechnical serviceability, that is focusing first and foremost on settlements, with due consideration of the structural ultimate limit state, is to strike a balance between theoretical rigor and ease of use in routine design practice. Although I've spent a good part of my life in academia, both full-time and part-time, I am and have always been a practitioner at heart. That's how I started my professional career. And even when I was in academia, I was always involved in design practice, and I am still involved in design practice to the present. So that practical element has always been very important to me in any research I've ever done. I'm sure that all of us have seen this quote by Einstein, maybe not in the exact words of Einstein here, but in some form of it. I'll give you a second to read it before I continue on. This quote of Einstein has been paraphrased by others as the aphorism, "Make things as simple as possible, but no simpler." But I think for the purposes of this presentation, this is better stated as, "Make things as simple as necessary, but no simpler." All right? And what I mean by necessary is that ease of use and simple never, in my opinion, should justify ignoring essential facts, which in this case includes residual loads from installation, down drag and drag loads from global settlements, group behavior where relevant, and of course, if we have energy piles, it needs to consider thermomechanical behavior as well. So again, ease of use and simple doesn't mean that we ignore essential parts of a problem. And hopefully by now I've shown you that including things such as residual loads from installation and the effects of global settlement are essential parts of the problem. Well, let me now move on to give you an overview of what I'm going to be talking about in the rest of this presentation module. As I said, although deep foundation elements are most often used in groups, especially in terrestrial applications, a deep foundation element design methodology and method that focuses on geotechnical serviceability, settlement, needs to include and begin with a robust analytical model and solution methodology and method for the baseline problem of a single deep foundation element. It remains a useful task to be able to make sure we come up with a model and solution that can replicate a static load test. Consequently, most of the remaining portion of this presentation module is devoted to modeling the axial load versus displacement behavior of a single deep foundation element within the broad conceptual context of Frobenius's unified method that states that there must always be vertical force and vertical displacement equilibrium of the deep foundation ground system at the equilibrium plane. Now, the physical and analytical model I've chosen for use is a theory of linear elasticity problem that consists of concentric vertical cylinders, as illustrated here. This is taken from a Federal Highway Administration report 19 years ago. So you have a system of an infinite number of concentric vertical cylinders of solid material, and these cylinders surround a hollow core, right? So this is a hollow core. And we have these, only two cylinders are shown here, but there is an infinite number extending radially. And this hollow core is oriented parallel and concentric with the vertical center line of the problem, which in this case is the y-axis. Now, the interior surface of the innermost solid cylinder that is in contact with the hollow core is subjected to a vertical shear stress tau naught. And that shear stress is applied at a distance r0 from the y-axis. So r0 is the radius of the hollow core. All right, here's r0 here. This applied shear stress tau naught then radiates horizontally from the point of application. All right, it's transmitted vertical shearing through all of these cylinders for some as yet unspecified radial distance. And it becomes an ever decreasing vertical shear stress tau within the solid material surrounding the hollow core. So these vertical cylinders are simply used to discretize, if you will, the elastic continuum that surrounds this hollow core. All right, so these concentric cylinders are just an artificial means to be able to break this up into finite pieces. I call this the concentric cylinders model. Now, in the context of this presentation, the concentric cylinders model represents the shear stress tau 0 that is applied to the soil by the shaft of the deep foundation element with a depth-wise constant radius r0 at the depth foundation element soil interface when the deep foundation element is externally loaded in axial compression. So if we load this in axial compression, tau 0 becomes the pile shaft dragging down, if you will, on the face of the innermost elastic cylinder. Not shown in this graphic is that tau 0 acting upward is also the positive shaft friction acting on the deep foundation element as geotechnical resistance to the externally applied axial compressive load. So tau 0 in this case is basically indicates the shear stress applied to the elastic continuum. Of course, there's going to be an equal and opposite tau 0 acting as resistance to the deep foundation element shaft. Now, although not considered in the literature to date, because this is an elastic model, it can be, and subsequently in this presentation model, applied to problems involving externally applied uplift loads. All right, so there's no reason that we could not, instead of this being a compressive load, that this was a tensile or uplift load, in which case, obviously, the direction of tau 0 is going to be reversed from that shown in the graphic. Now, the concentric cylinders model, this is one of those things that's been hiding in plain sight. It was first proposed about 50 years ago, and I chose it for use for several reasons. First of all, it provides a unified physical model and theoretical basis for several different analytical methods that collectively produce a variety of relevant calculated outcomes for deep foundation element stresses, forces, and displacements. Now, where appropriate, these analytical methods can include consideration of residual loads from installation, the effects of post-installation global settlement, and the thermomechanical behavior of energy piles. This concentric cylinders model has model parameters that are common solve properties. So the parameters are not some mysterious quantity, they're common solve properties. So lend themselves to straightforward quantification using post-process data from modern site characterization tools such as the pisocone and seismic pisocone. Now, it's important to note that this post-processing requires nothing more than generic commercially available spreadsheet software. You could actually do it by hand calculation, and I've done this just to satisfy myself. But the sheer volume of data that you typically get from a modern pisocone or seismic pisocone sounding really makes manual calculation impractical in actual applications. The concentric cylinders model lends itself to straightforward modification for modeling nonlinear soil behavior using a variety of mathematical strategies and techniques. And many of these are also solvable using generic commercially available spreadsheet software. And finally, the concentric cylinders model has shown promise as a physical and analytical model for including the behavior of taper deep foundation elements by allowing R0, instead of being held as a constant, to vary with depth and therefore include radial displacement as a variable in the problem formulation and solution. So the bottom line is this: the concentric cylinders model has a lot going for it. It really checks all the boxes and fits the bill for what I feel needs to be done. So after I talk about the concentric cylinders model and applying it to a single deep foundation element, I'm going to follow this up with a discussion of group behavior, and I'm going to use the narrow group versus wide group categories used by Fellenius to define group behavior. Now, while the dividing line between narrow and wide deep foundation groups is arbitrary, it is based on Fellenius's many decades of first-hand experience with deep foundation elements. In addition, Fellenius, in his annual Red Book, explains his rationale for defining each category. So the categories are not just something he pulled out of thin air. Each of these categories has really quantifiable behavior and other rational metrics. So in my opinion, I think Fellenius's definition of group behavior represent a coherent, defensible, up-to-date treatment of this subject. And I'm going to conclude this presentation module with a denouement in the form of discussion of several case histories, and I will illustrate application of an analytical model that I came up with based on the concentric cylinders model and that I solved with a spreadsheet that I developed myself. So hopefully by the time this module is completed, I will show you that we have a very viable model, that it is eminently practical to use today in the present, using nothing more than commercially available generic spreadsheet software. I happen to use Microsoft Excel. If you have some other software or spreadsheet software you use, that's fine as well. So let me now move on to the heart of this module. Most of the discussion is going to focus on single deep foundation element behavior. As you can see, I've broken it up into several subsegments. And let me first begin with some further discussion of Frobenius's unified method. Now, the overarching precept of this presentation is that the analysis and design of deep foundation elements, both individually and in groups, for axial loads, needs to be dealt with in the holistic manner of dealing with any soil structure interaction problem. This means simultaneously and interactively considering both the vertical displacement and vertical force components of a deep foundation ground system, and the fact that both of these components must always be in equilibrium from the time that a deep foundation element is installed or constructed in the ground through the entire service life of a structure supported by a deep foundation element ground system. Now, as I noted at the beginning of this presentation, this precept is neither new nor my own unique opinion, but falls under the broad concept of what is called the unified method that was first proposed in publications in the 1980s by Professor Frobenius. It's relevant to note that in the approximately 40 years that the unified method has been known to the public, computational technology has gone from slide rules to the personal, or what we used to call pocket calculators, to personal computers that are capable of running very sophisticated software. During the same time frame, there have been substantial advances in geotechnology related to site characterization, as well as from research and development into deep foundation behavior in general, and use of the unified method in particular. Frobenius has been, and co-workers have been very prolific in publishing papers that illustrate use of the unified method. Now, this technological evolution and advancement has in turn resulted in considerable evolution of and mission creep in what exactly constitutes the unified method. And it appears to me that components of the unified method have been modified and added over time in a bit of a patchwork fashion. Now, even in Frobenius's own textbook, the so-called Red Book, that has been available online in digital format for several years now, and that at least up until this year he has updated annually. Treatment of the unified method is really scattered throughout several chapters and sections of chapters. So, I mean, I've looked at the Red Book several editions now over the span of many years, but I found it difficult to define even exactly what constitutes the unified method these days. Now, by comparison, Frobenius's 1988 paper on the unified method that was published by the Transportation Research Board was only 8 pages long. Consequently, the unified method at the present time is best viewed as an umbrella concept that encompasses a wide range of different analytical capabilities that have as a common element the overarching precept that a deep foundation element, whether acting alone or as part of a group, and the surrounding ground comprise a single integrated system of vertical displacements and vertical forces that must always be in static equilibrium. Furthermore, this equilibrium can vary with time, either continuously or episodically as a result of a wide range of anthropogenic and natural events, as I've talked about in the preceding Phase 1 module. Now, for the purposes of this presentation, it's important to understand a couple of things. First of all, not all the analytical capabilities that appear to constitute the current version of the unified method need to be used in every application. For some of these analytical capabilities, different specific theoretical solutions can be used in many cases. Although in his publications, Frobenius typically only mentions one solution method that I assume reflects his professional opinion as to what is a quote-unquote best method at the time of publication. As a result, users of the unified method have some latitude with respect to the analytical features they want to use and how to implement these features theoretically and mathematically. Only aspects of the unified method that I deem relevant to the primary goals of this presentation and that I personally believe are best suited to fulfill those goals will be discussed, focusing initially on the behavior of an individual deep foundation element. Again, this is for the reasons I said earlier in this module, that we, as a minimum, need to make sure whatever analytical model we come up with can reasonably replicate a static pile load test before we go on to apply that to group behavior. Most of my time will be spent discussing the behavior of an individual deep foundation element, although I will touch on group behavior later in this module. Now, for the purposes of this presentation, the basic concept of the unified method, or at least what I feel is the basic concept of the unified method, which is linking vertical forces and vertical displacements in the deep foundation ground system at all times using the concept of an equilibrium plane. This basic concept or basic element of the unified method has not changed since Fellenius first wrote about it in the 1980s, and I'll show you why I feel that way. This is from his 1988 Transportation Research Board paper. You're going to see figures like this several times in this module, so let's discuss what they are. Here we're looking at the load in a deep foundation element as a function of depth. And here we're looking at settlement as a function of depth. And this settlement plot is used to illustrate both the ground settlement as well as the deep foundation settlement. So in this case, the dashed curve is the ground settlement. The solid curve is the deep foundation settlement. So you see here, the ground is settling more than the deep foundation. At the neutral plane, what we call now the equilibrium plane, the settlement to the ground, the deep foundation are the same. Now below here, the ground settles less, but the deep foundation element settles more. And this is to develop toe resistance and positive shear friction. And again, here we see, here's the dead load applied to the head of the deep foundation element. The force within the deep foundation element increases due to negative shear friction. All right, that's because here the settlement is greater than the deep foundation element, so we have negative shear friction that produces down drag. So we have a drag load increasing till we get to the neutral plane, and then the load in the deep foundation element decreases, and we of course have some toe resistance. And as we can see, both the forces as well as the displacements must always be in agreement at the equilibrium plane. So this is what Fellenius showed almost 40 years ago, and this is from his current version of his red book. And aside from the fact that there's some additional graphs and curves shown, these are basically the same diagram. All right, here's the load in the deep foundation element shaft as a function of depth. Here's the settlement. The ground settlement with the blue curve, the deep foundation settlement with the red curve. Certainly nowadays that we can show colors in publications makes curves easier to portray and to look at. All right, so we're looking at basically, what I'm trying to show you is this is the basic concept to me. This is the basic concept of the unified method, that force and displacement of a deep foundation ground system must always be in vertical static equilibrium at all times for the life of the structure. If the settlement of the ground changes, as I showed you in a case history from Japan in the preceding module, well then the deep foundation element has to change as well. But everything comes together at the equilibrium plane. And we've seen already that even with the energy piles, that the equilibrium plane is a unifying concept for things. So what I'm trying to show you with this slide is that what I feel is the key element of the unified method, the key element that I'm going to focus on in the remainder of this module, really has not changed at all in the life of the unified method. So again, there's a load, there's a settlement, and they all come together at the equilibrium plane. Now, the preferred starting point, the initial analytical case for using the unified method, is always to first define the depth-wise profile of residual loads from installation with no externally applied load. And we want to focus on, in this case, this is the it says before construction, construction meaning construction of the overlying structure. All right, so this is the curve of residual load in this deep foundation element in this qualitative illustration. Of course, zero load at the head of the deep foundation element builds up and then decreases. Now, in this qualitative example, there's a relatively small residual load at the toe, although as we've seen, in actual cases, the residual toe load is substantial and it can approach 100% of the ultimate toe resistance for certainly driven tapered piles. Now, by definition, the vertical displacement of the deep foundation element is depth-wise zero under this initial condition of residual loads. So we're not really looking at the settlement curve here. Although there's initially forces in the deep foundation element shaft, because there's no structure attached to it, we zero the settlement plot under this condition, at least initially. So we only have to consider for residual loads only the vertical force equilibrium along the deep foundation soil interface, and the equilibrium plane in this plot is not shown explicitly, but would typically be somewhere between about 15 and 20 meters. You could see the peak of this curve is somewhere here between 15 and 20 meters. Well, then next we consider the vertical displacements and forces and equilibrium plane under the condition of an externally applied load equal to the unfactored service dead load, QD. And as we show here, we went from no load after installation, now we apply the dead load, and we now have to satisfy both force and settlement equilibrium. So modeling the elastic compression of the deep foundation element shaft as well as the TZ QW behavior of the deep foundation element is required for analyzing this design case, with the QW component here at the toe of much greater importance as toe resistance is relatively sensitive to toe settlement. Now in this example, the service dead load is resisted entirely by reversing the deep foundation soil interface shear stress along the upper portion of the shaft. Okay, up here after installation we have negative shaft friction until we get to the equilibrium plane, and we see what's happened after we apply the dead load. This negative shaft friction has converted to positive shaft friction of resistance, and essentially nothing has happened to this lower portion of the shaft or at the toe. Now, although not shown here, under the application of the dead load, the equilibrium plane moves up to the ground surface. However, as I showed you with the Holman Island piles in Norway, application of the dead load in Norway did not remove all the negative shaft friction from installation. Okay, I showed you this slide previously. Under these are the Holman Island constant diameter pile. Under the maximum service load, which is this right curve here, we still have some negative shaft friction. Equilibrium plane is below the ground surface, and the maximum load in the shaft is actually greater, of course, at the equilibrium plane than is applied. So all I'm trying to show you here is that curve in Fellinius's Red Book is simplistic. Application of the service load, the design dead load, does not necessarily remove all the negative shaft friction from residual load. It did in Fellinius's simplistic graph, but certainly in the real world it does not. And we see that here in the Holman Island test piles in Norway. Now, on projects where global settlements can occur, either from long-term static loading of the ground surface or short-term dynamic loading due to an earthquake, an additional analytical case requires assessment, as global settlements can result in relatively significant changes in deep foundation element settlement, downdrag, as well as maximum vertical force within the deep foundation element shaft, with a significant change in the location to equilibrium plane. So what we're saying here is, okay, at the time the deep foundation element was installed, we had these residual loads, okay? And then we build the structure and we apply the dead load, and the force in the deep foundation shaft becomes this. And in the process, the equilibrium plane goes from somewhere around here up to the ground surface. Now it's assumed that over time, we have, was shown here, about 150 millimeters, roughly 6 inches of surface settlement, and here's the settlement profile. So now things are going to change because of the downdrag that the soil settlement imparts. So now, immediately after application of the dead load, this was the force in the deep foundation element shaft. Now we're going to have drag load develop in the upper portion of the shaft. So as this settlement occurs, the equilibrium plane is going to move downward again, in this case to about 16 meters. And now the force in the deep foundation shaft is going to increase from the surface to the equilibrium plane and down to the toe. Notice that the toe load has had to increase substantially. The toe load after installation was relatively small, but now the toe load has had to increase substantially in order to resist the drag load in the upper portion of the shaft. And as a result, the deep foundation element has settled as well. In this case, looks to be about 40 millimeters, so something a little bit more than 1.5 inches, let's say. And again, we have to establish a force as well as settlement equilibrium at the equilibrium plane. And these graphs down here are just showing you that the way that the drag load caused by this settlement over time in the life of this deep foundation element, the way that this drag load is resisted, since we've already mobilized all the positive shaft friction down here, we can only accommodate this drag load by mobilizing a lot more toe resistance. And this is the QZ, this is the load settlement relationship for the deep foundation element toe. And you see it plays a crucial role here in determining how much the toe is going to settle, and therefore how much the rest of the deep foundation element is going to settle. Okay, the toe settlement had to go from 0 to this value, which looks to be maybe 35 millimeters. Because between the toe and the ground surface, we're just going to get elastic compression of the pile of the deep foundation element shaft. So most of this additional settlement of the head of the deep foundation element is the result of significant toe settlement to mobilize significant toe resistance so that we can establish vertical force equilibrium under the drag load. I will show you some worked out examples in the denouement section of this module later on that illustrate this a little bit more clearly. So again, it's the post-installation settlement, the global settlement, has resulted in the equilibrium plane moving from the ground surface down along the shaft and results in relatively significant pile head settlement. All right, so as I said, in this qualitative example, the global settlement results in substantial increase in toe resistance relative to that existed at the time after the installation, and this increase in toe resistance is necessary to compensate for the substantial increase in unit drag load along this upper 16 meters of the deep foundation element shaft. That is the direct result of down drag caused by these rather significant 150 millimeters, roughly 6 inches of global settlement at the surface. Now, there are several items to note and emphasize when analyzing this global settlement design case. I've touched on some of them, but want to talk about some of them in greater detail because they are very important, as we'll see later on. Now, first of all, vertical displacements and forces and the equilibrium plane are determined under the condition of an externally applied load equal to the unfactored service dead load. Depending on the source of the global settlements, the geotechnical resistance of the deep foundation element may need to be recalculated due to changes in the vertical effective stress in the ground around the deep foundation element brought about by whatever mechanism caused the global settlements. I think in this simple qualitative example Fellinius used in his textbook, this was not done, but certainly this is something that needs to be done in practice. The structural adequacy of the deep foundation element needs to be checked. Again, noting that when you have global settlements, the peak axial force in the deep foundation element is not at the ground surface, where we normally assume it is, but at some greater depth. And again, it's worth noting that you have to be careful that the peak stress in the deep foundation element may or may not occur at the equilibrium plane. Certainly in the case of tapered deep foundation elements, that maximum stress is going to be much lower. It's going to be fairly close to the toe. All right, so again, although the maximum compressive force in the deep foundation element will always occur at the depth of the equilibrium plane, the maximum compressive normal stress may occur at a different depth, and that depth is usually near the toe. If the deep foundation element has a depth-wise variable perimeter, such as with a tapered deep foundation element. Now, an essential mission-critical component of designing deep foundation elements based primarily on the geotechnical serviceability limit state within this broad context of Fellinius's unified method is mathematically defining the TZ and QW behavior of an individual deep foundation element. Now, as I pointed out earlier, and you can see in this graphic, the QW force settlement behavior at the toe of the deep foundation element is of particular importance for defining the location of the equilibrium plane. And this is because the only way that the deep foundation element can compensate for the drag load applied in the upper portion of the shaft is by increasing the toe resistance, as you could see here. Now, given the essential nature of TZ-QW behavior in routine design practice, whatever method is chosen for you should take full advantage of state of knowledge soil behavior and site characterization technology, yet be practical to implement. Not every project, obviously, in routine design practice has the available time and necessary financial resources to be turned into a research project where the necessary TZ, QW model parameters can only be determined from instrument and static load tests that is performed during the design phase and prior to the construction phase. And I'm emphasizing this because if you look at Fellinius's current edition of his Red Book, he basically says, well, yes, the TZ and especially the Q, he call it QZ here, but I call it capital QW. QW relationship is especially important to define, yet in his Red Book, Fellinius says, well, the only way you could do that is you have to run some instrumented load tests and you have to use this very complicated curve fitting technique to come up with this mathematical relationship. That's very elegant, but it's very impractical. Okay, I think this is where we need to step back and get real about things. We need to strike this balance between practicality and ease of use and theoretical rigor. So we need to come up, what I'm getting at is we need to come up with a way to be able to forecast this TZ-QW behavior, but not by running instrumented static load tests in advance of the construction process. That's just not going to happen in the real world, and we all know that. Now, in addition, given the fact that it is now well known that residual loads exist for most, if not all, types of deep foundation elements, and that they can be relatively significant for common types of deep foundation elements such as driven piles, whatever TZ-QW method is chosen or developed for use should be capable of incorporating this residual load behavior into its mathematical and solution formulation. First of all, whatever TZ-QW model we come up with, the TZ springs that model shaft resistance need to model both positive and negative shaft friction and be able to seamlessly transition from one stress state to the other. This is not something that Fellinius touches on at all in his Red Book. We need to allow the QW spring that models toe resistance to have a non-zero initial value at zero displacement to represent the initial toe resistance from residual load. Again, this is not something that Fellinius illustrates in his Red Book. So the topics that follow in this module illustrate the theoretical basis for a TZ-QW physical and mathematical model and the resultant solution that taken together comprise a TZ-QW analytical method that meets all of these criteria in my professional opinion. What I'm going to be showing you in the following segments is how we can come up with a TZ-QW physical and mathematical model that is easy to use in routine practice, satisfies the requirement to be able to handle residual loads, and could be solved with nothing more than a spreadsheet. Well, perhaps it's no surprise the core component of this proposed analytical method I'm going to show you is this concentric cylinders model that I introduced earlier in this module. I mean, that was obviously the reason that I introduced it, is now I'm going to make extensive use of it. And as I pointed out, this concentric cylinders model has been known, discussed, and used in the published literature for several decades. So it represents well-established science, and I think that's very important to give us a level of comfort to use it. Now, the novel aspects of the TZ-QW analytical method I'm going to show you is how this established science of the concentric cylinders model is incorporated into the TZ-QW methodology, as well as how the post-process outcomes of site characterization using seismic piezo-cone soundings are used to quantify the necessary method parameters. So even though the concentric cylinders model has been around for several decades, what I'm going to show you is we need to make some, I think, some clever modifications to it to create a usable TZQW method. Well, I've already touched on the basic elements of the concentric cylinders elastic model, but I now want to go through some aspects of it in greater detail. Now, the earliest application of the theory of linear elasticity to deep foundation elements was in the latter decades of the 20th century and involved use of Mindlin solutions from the 1930s for a point load within an elastic half space. So Mindlin solutions were basically variants or extensions of the well-known Boussinesq solution. As we know, Boussinesq solution was for a vertical point load on the surface of a half space. Mindlin solved two problems for a point load within a half space, both vertical and horizontal point loads. So these Mindlin solutions were used to model deep foundations subjected to axial and lateral loading, respectively. Issues associated with using the vertical point load Mindlin problem to model deep foundations subjected to axial load include the fact that there is an inherent difficulty of successfully using a linear elastic model for a geostructural application where the material behavior, soil in this case, is always nonlinear elastoplastic. The point load, which represents in this case the axial force within a deep foundation shaft, is physically attached to the elastic continuum, which is the soil. And this meant that the slip, that is the relative displacement between a deep foundation element shaft and adjacent soil, when the unit shaft resistance is fully mobilized, is not modeled. It has to be approximated in other ways. So as a result of these and other significant technical issues, experience has shown that deep foundation element analytical models based on the Mindlin problem have never seen widespread routine use in design practice. They've been covered extensively in textbooks. If you look at the Poulos and Davis book on pile foundations from decades ago, these researchers used the Mindlin solution quite a bit, and a good part of their book discusses application to deep foundations. Now, the much more promising, I think, elastic model was developed and saw initial use also in the latter decades of the 20th century. And this is the so-called concentric cylinders model that, as I pointed out earlier, models the vertical interface shear stress between a deep foundation element and adjacent soil. So we're not modeling the load in the deep foundation element, we're modeling the interface shear stress. And as I pointed out previously, the concentric cylinders model assumes that the deep foundation element shaft produces a vertical shear stress, tau 0, on the adjacent soil that acts in a downward direction in the more common case of an externally applied axial compressive load. And then this vertical shear stress radiates outward horizontally as a vertical shear stress that decays throughout the elastic mass around the shaft. Now, this vertical shear stress produces a vertical shear strain within the soil mass, which in turn produces a surface settlement of the soil mass. Now, an essential part of developing a practice-oriented solution for the concentric cylinders model has been research to empirically define a radial distance from the deep foundation element at which this surface settlement can be assumed to be negligibly small in magnitude. And this has been done already by prior research in the UK. Note that the overall physical behavior of the soil mass surrounding a deep foundation element that is modeled by the concentric cylinders model is completely consistent with research that has shown that the load transfer between a deep foundation element shaft subjected to externally applied axial load and the surrounding soil occurs as vertical shearing within a zone of soil and not as a simple planar slippage between the shaft and soil interface as has been assumed historically. And I showed you this in earlier in this presentation, where what really occurs when you load a deep foundation element in axial compression is that you develop a shear zone, not a planar shearing along the contact between the deep foundation element shaft and surrounding ground. You develop a shear zone. And you also get a surface settlement profile. It's hard to see. This brown dash curve here on either side is the surface settlement profile. You get the settlement trough develops adjacent to the deep foundation element shaft as a result of this vertical shearing. Now, both of these behaviors are completely captured by the concentric cylinders model. And that's a very important thing to consider, that this concentric cylinders model really does a very good job of matching qualitatively what exactly happens when you load a deep foundation element in axial compression. So this really indicates, I think, that we're on the right track with the concentric cylinders model, because it does a good job of capturing and replicating actual observed behavior of what goes on between a deep foundation element and the surrounding ground. And this is one of several reasons why I chose this model to explore further. Note that because the concentric cylinders model models the deep foundation element soil interface shear stress as opposed to the force within the deep foundation element, we no longer have this slip issue. We can easily deal with the interface slip based on the model that we choose to model the shear stress. We can use a wide variety of interface shear behaviors: elastic versus elastic plastic, linear versus nonlinear. So we no longer have the limitation of the slip issue we have with using the Mindlin solution. Note also that the concentric cylinders model, as originally formulated and used to date, that, as I pointed out previously, acts vertically downward on the soil adjacent to the deep foundation element. And this corresponds to positive shaft resistance and the unit shaft resistance due to sliding friction. However, because this is an elastic model, there's no reason why we can't reverse the direction of tau zero to simulate negative shaft friction from either unit drag load or resistance to uplift loading. So this is something that I extended the model to do, and that is we can certainly reverse the direction of tau zero because this is a linear elastic model. So we can simply reverse this to capture other behaviors that we need to or want to capture, like drag load and resistance to uplift loading. Now, there are several ways in which the concentric cylinders model can be used with deep foundation elements, and I'm going to discuss each of these in detail in the following presentation segments. And I've arranged these in order of their historical evolution, beginning with what is called the Randolph-Roth problem. The first deep foundation application of the concentric cylinders model that I'm aware of was the so-called Randolph-Roth problem that first appeared in the published literature in the late 1970s as one of the outcomes of the doctoral research of Professor Mark Randolph at the University of Cambridge. As he formulated, this is a two-layer elastic problem, formulated originally in terms of Young's modulus of the soil around the deep foundation element shaft, as well as below the toe. As you can see, this is the basic model, as you can see from this graphic. Now, Young's modulus for each of the two elastic layers was allowed to vary as shown, that is, linear within layer 1 and uniform with depth within layer 2, but at a given depth was assumed to remain constant in magnitude and independent of the applied downward acting axial load at the head of the deep foundation element. By the way, note that the concentric cylinders model was only used to model the shaft resistance. The toe resistance was modeled as a rigid disk bearing on an isotropic homogeneous elastic layer of infinite depth. Now, as part of Professor Niazi's doctoral research at Georgia Tech, under the direction of Professor Main, the Randolph-Roth problem formulation was changed to use shear modulus instead of Young's modulus. And as we'll see, this turned out to be actually a meaningful and useful change for a number of reasons. First of all, shear modulus is more consistent with the basic physical concept of the concentric cylinders model that models shaft resistance of a deep foundation element as being governed exclusively by radially decreasing vertical shear stresses and concomitant vertical shear strains, and the resulting vertical displacements within the ground surrounding a deep foundation element. Use of the shear modulus allows use of state-of-practice site characterization methodologies, such as the seismic piezo cone, that measure site-specific values of the small strain shear modulus Gmax in situ. Now, the basic use of the Randolph-Roth problem solution is to simulate the results of a traditional static load test. So you want to generate a curve of applied load versus pile head settlement for some assumed deep foundation element geometry and some site-specific ground stiffness as defined by what is called the operative shear modulus G sub L. Now, this concise table is from Niazi's dissertation, doctoral dissertation. There is what's called a rigid pile solution and compressible pile solution. These equations look very complex, but they're just algebra. There's just a wide variety of parameters to define, and if you get a copy of Niazi's dissertation, it's available online at no cost. All of the parameters are very clearly defined how to quantify. Trust me, I've used this now for several years. You need nothing more than a spreadsheet solution. You could do this by hand calculation if you wanted, but it simply becomes ponderous. It's easiest to do with just a simple spreadsheet solution. All right, so you assume an applied load Q from your site-specific site characterization. You have a shear modulus variation, and then you calculate the settlement at the head of the deep foundation element. And you simply repeat this for different loads. Now, you can make separate estimates of the toe resistance and the toe settlement for a given magnitude of settlement at the head of the deep foundation element. Now, as I said, I've used this actually for several years now, and I found that there are some real significant limitations. First of all, the Randolph-Roth problem assumes a typical Whiston-Place deep foundation element with zero initial resistance between the deep foundation element and the ground. All right, so residual loads from installation, which we know now exist, are inherently neglected. It certainly does not allow directly for consideration the effects of post-installation global settlement, and it does not lend itself to extension to group behavior. Now, regardless of whether you use the original Young's modulus or the later shear modulus in its formulation, the single most significant shortcoming of the Randolph-Roth problem and its solution as originally implemented is that the saw module around and below a deep foundation element are assumed to be independent of the magnitude of the externally applied load. So this implies linear elastic behavior for both the deep foundation element shaft and toe resistance components, as well as the overall deep foundation load settlement behavior, and thus ignores the actual nonlinear behavior of both the shaft and toe resistance components that when combined result in the overall nonlinear load settlement behavior of actual deep foundation elements. So as originally formulated, the Randolph-Roth problem is really, in my opinion, an academic curiosity. It doesn't replicate the actual nonlinear load settlement behavior of deep foundations. And I think because of this poor representation of actual deep foundation element behavior, the Randolph-Roth problem, as originally formulated and implemented, remained, I think, an academic curiosity of no practical use from the late 1970s until the early years of this century, when Professor Paul Main at Georgia Tech made what I think are some game-changing modifications to allow us to implement nonlinear behavior into the Randolph-Roth problem. These modifications made use of mathematical modeling of what is called modulus degradation. Modulus degradation is just another name for modulus reduction. And if we combine modulus degradation with the use of the small strain shear moduli as measured in situ with, say, for example, a seismic piezo cone, we now can move the Randolph-Roth problem from being an academic curiosity to a tool that has some practical applications in routine design practice. So in order to illustrate this, we need to talk about nonlinear analysis using modulus degradation. Some of you may already be familiar with this from other applications, but for the benefit of those who may not be familiar with it, I will go through this in some detail. So to begin with, modulus degradation can be formulated for either Young's modulus or shear modulus to occur as a function of either force, stress, or strain displacement, depending on the desired formulation of the resulting mathematical model and the application-specific way that this mathematical model is implemented into a solution algorithm. You can also produce either a tangent modulus or a secant modulus, again depending on the desired mathematical model and the application-specific way that this model is implemented in a design algorithm. And again, as we know, a tangent modulus, let's say we're trying to replicate this red curve, this load settlement curve shown in red. A tangent modulus, you would do this in a series of linear steps. That is essentially the tangent of this curve at a given point along the curve. An alternative formulation is to do a secant approach, where we simply always starting from zero, we try to forecast points along the curve. Okay, so you get pretty much the same result either way. It's simply whether you use one or the other. It really depends on the solution algorithm that you're looking for. Now, Main's modifications to the Randolph-Roth problem solution, which first appeared earlier in this century, have several components, but the single most important one is modeling the nonlinearity of both the shaft and toe resistance components using a modulus degradation methodology that is based on a repeated application of a secant modulus approach in order to get a problem solution. Now, the specific modulus degradation method or formula that Main used was first proposed by Fahey and Carter in the 1990s and is based on an assumed hyperbolic shape relationship that uses two empirical model parameters called f and g, and these control the shape of the hyperbolic curve to produce the desired results. So these are dimensionless empirical parameters that we choose in order to shape the hyperbola to meet typically some set of data. Now, although Maine initially applied the Fahey-Carter modulus degradation equation to the original Randolph-Roth problem formulation based on Young's modulus, later on this century he changed it to using the shear modulus as developed by Niazi, who was Professor Maine's doctoral student at the time. And one of the good things about changing it to shear modulus, in addition to the fact that it better matches the shear behavior soil that we're trying to capture, is that it allows direct use of the small strain shear modulus, G max. Some of you may know this as G naught, that is measured in seismic pisocone soundings based on the shear wave velocities. And the seismic pisocone was beginning to see widespread use in routine design practice in the early years of this century. So here's the Fahey-Carter modulus degradation equation as used with solutions to the Randolph-Roth problem. We have a ratio of the secant modulus to G max. G max again comes from shear wave velocity measurements made in a seismic pisocone or some other in situ testing device. We have the F and G shape parameters, and we normalize the load to the ultimate geotechnical resistance. So note that we still have to come up with calculating the ultimate geotechnical resistance in order to make use of this model. That's a very important point to bring up. All right, and then you simply take the solutions that I showed you previously from, in this case, from Niazi's doctoral dissertation. And we're going to be using secant moduli. So we choose a load Q. We go in and we calculate from this equation a ratio of G secant to G max. That gives us the operative shear modulus, which also we use in this equation. And as a final result, this gives us settlement at the head of the deep foundation element. And we would repeat this process in order to generate the complete load settlement curve. Now, I've used this Randolph-Roth problem solution together with the Fahey-Carter modulus reduction equation and G max measured in seismic pisocone soundings, quite a few case history piles from Kennedy Airport, and I've developed the following observations. First of all, the accuracy of the calculated load settlement curve, when compared to measured results in a conventional static load test that is performed correctly, emphasis on the correctly, is very dependent on the accuracy of the calculated value of the geotechnical ultimate limit state of the deep foundation element, QU. And as I showed you in a prior slide, you need this in order to use the Fahey-Carter equation. However, the shaping parameters, F and G of the Fahey-Carter model, also have a noticeable effect. But the single most important thing is unless you accurately estimate the geotechnical ultimate resistance of a deep foundation element, whatever curve you generate using the Fahey-Carter Randolph-Roth procedure is not going to be worthwhile. Now, even if the overall load settlement curve is a good match to actual measured behavior, the accuracy of the separate curves for shaft and toe resistance versus settlement can be inaccurate, sometimes significantly so. And actually, in my experience, they're almost always inaccurate. This seems to be generally the case for predominantly coarse-grained soil profiles, which is what I was most interested in, where shaft resistance tends to be grossly overestimated and toe resistance grossly underestimated. The fact that residual loads from installation are neglected in the Randolph-Roth problem appears to be at least part of the reason for this disconnect between calculated and measured results. I think another part is the fact that even though you're modeling modulus degradation, you assume that the shaft and toe resistances are going to degrade at the same rate. And this is simply not a reflection of actual behavior. So the conclusion I reached some years ago as the result of my independent research is that the Randolph-Roth problem solution, when used in its traditional manner to forecast overall load settlement behavior at the head of a single deep foundation element, is an easy-to-use spreadsheet solution analytical method, and it can produce a reasonable overall load settlement curve for a single deep foundation element, but only if you have a reasonably accurate forecast of the geotechnical ultimate limit state that you've determined beforehand. However, the separate forecast of shaft and toe resistance versus settlement that are calculated using this methodology can be significantly in error. So in my experience, should not as a rule be used unless you've been able to convince yourself that based on site, project, and deep foundation element specific basis, these measurements from instrument and static load test match what you calculate from the Randolph-Roth problem Fahey-Carter methodology. Additional conclusions I reach is that the various components of the Randolph-Roth problem and its solution, such as the concentric cylinders model and the Fahey-Carter modulus degradation model, have individually and used in different way proved useful to incorporate into other analytical methodologies that are used to model the response of deep foundation elements to actually applied loads. So what I'm saying here is that the overall problem I found is that the Randolph-Roth problem itself, it's interesting and easy to use, but I think has limited use. However, if we use the concentric cylinders model and if we use the Fahey-Carter modulus degradation model separately and independently in other solutions, we get much better results. And that's what I'm going to be talking about next. So in the next presentation segment, what I'm going to be doing is I haven't given up on the concentric cylinders model and the Fahey-Carter model. I'm just going to use them in a different way. And I think, as you'll see, we get much better results from this. I now want to move on to what I think is the most important segment of this module. In fact, perhaps the most important segment of this entire presentation. And that is to show you how we can take a bunch of different concepts and ideas that I've shown you so far in this presentation and incorporate them into the well-known TZQW methodology to produce a new analytical model. And this analytical model is something that requires nothing more than a spreadsheet for solution. It can be used with existing technology by any design professional or academician anywhere in the world. And I believe that this will be a real game changer. It will allow us to change the way in which we design deep foundation elements for axial load. All right, I think this will give us guidance as how we can make some very meaningful changes in the way that we do things, which is the overall goal of this presentation. Now, as you probably know, the TZQW methodology is based on a physical model that is the static equivalent of the one-dimensional wave equation as applied to deep foundation elements. What we do is we take a deep foundation shaft and we divide it into an arbitrary number of artificial segments with the average shaft resistance, which is a shear stress, due to sliding friction of each segment, that's the T part, modeled as a helical or coil spring that is oriented parallel to the deep foundation element shaft, and that segment displaces an average distance Z for that segment. So that's where the T and the Z come from. The lowermost segment is also supported by a helical spring acting in end bearing and displacing a distance W to model the toe resistance, which is a force, which is the capital Q, and that's the QW part here. So TZQW simply refers to the notation for the resistance and displacement of the segments in shaft friction due to sliding friction and end bearing. Now, the TZQW methodology is sometimes referred to as the load transfer methodology. I think this is somewhat of a misnomer, as any methodology for calculating the load settlement behavior of a deep foundation element involves the generic mechanism of load transfer. In addition to alternative terminology, it's very common to see alternative notation for the TZ and QW, different letters, lowercase letters versus uppercase letters. So in the published literature, you will see this same methodology I'm talking about here, called by different names and given different notations. So I want to be clear as to what we're talking about here. Now, before proceeding further, it's relevant to the present discussion to highlight the fact that the traditional TZQW model assumes that each artificial segment only displaces vertically, and therefore shaft resistance only comes from the geotechnical resistance mode of sliding friction. This implies that there is no radial displacement of an artificial segment, and thus ignores the radial displacement due to the Poisson effect when a deep foundation element shaft is subjected to axial stresses, including the thermal-mechanical behavior of energy piles. It also ignores the radial displacement due to geometric effects when a tapered deep foundation element shaft is subjected to axial displacements. And both of these behaviors are discussed further later in this presentation segment. And I should point out at this time that you may have seen people, yes, of course, have used this methodology for driven tapered piles, and they do that by simply making the diameter of the different segments different. That, I think, should be obvious, does not capture the wedging behavior that occurs with a real tapered deep foundation element. Now, returning to the main discussion, development of the TZQW methodology dates back to at least the 1960s, and as best as I can tell, it was contemporaneous with development of the PY methodology for analyzing the low displacement behavior of deep foundations subjected to horizontal and moment loading. And both of these were, both the PY and the TZQW methodologies really were brought about by the development of offshore oil platforms, which began in the 1950s and really started to take off in the 1960s when digital computers became available, at least at research universities. However, the TZQW methodology has never achieved the universal level of usage of the PY methodology in either design practice or academic research. And I think a large part of that is the difficulty in quantifying the TZ and QW springs. As you may know, for the PY method, the way that they have been able to calibrate the PY springs is by running lateral load tests on deep foundation elements. And if you run a lateral load test on a deep foundation element and you model the horizontal load versus horizontal displacement at the head of the deep foundation element, you could do a pretty good job of coming up with empirical equations for the PY springs. Unfortunately, if you want to develop empirical equations for the TZQW springs, you now need to run instrumented static load tests. And it's far easier to run a lateral load test where you just measure horizontal load and horizontal displacement at the head of the deep foundation than it is to run axial loading static load tests. So there's never really been enough test data to generate databases for TZQW springs. People have done it. Yes, you will find there are any number of different methods out there where people have come up with purely empirical spring values. I think the attractive nature of what I'm going to illustrate to you in this segment is that there's nothing empirical here. We can develop these spring stiffnesses from site-specific site characterization and theoretical models. So as I said, there have been many different methods proposed over the last 60 plus years for modeling and quantifying the shaft and toe spring stiffnesses for the TZQW methodology. The common element of these different methods is that they each seek to model the inherently nonlinear behavior of both shaft and toe resistances in some manner. So you need to accept up front that these springs, both along the shaft and at the toe, will have nonlinear behavior. Now, regardless of the specific method used to model and quantify the shaft to toe spring stiffnesses, the typical solution algorithm consists of what we call a bottom-up analysis, where you assume a toe displacement, and this produces a unique value of the toe resistance force. Right? So you've already generated these QW and TZ curves. And then the solution progresses up the deep foundation element shaft by calculating the displacements at the top and bottom of each artificial segment. And from that, an average value of the shear stress T for each artificial segment. All right, you see how that goes. The vertical displacement and force at the top of the uppermost shaft segment represents the settlement and external force at the head of the deep foundation element. All right, these are the desired outcomes, because what you want to do is produce a QW curve for the head of the deep foundation element in order to mimic the results of a static load test. Now, understanding the basic solution algorithm that has been used historically is very important, because as we'll see as this segment progresses, that when we go to now deal with other load sources and settlement sources, we're probably going to have to rethink how we go about the solution algorithm. But this is very efficient for producing the basic fundamental outcome of a TZQW analysis, basically simulating the results of a static load test. So the process of assuming a toe displacement, calculating corresponding settlement, and working your way up the deep foundation element shaft to produce the force and settlement at the head is, as I said, the end result. Now, important points to emphasize about this traditional application of the TZQW methodology that are relevant to the subsequent discussions are the following. First of all, only the geotechnical mechanisms of shaft resistance due to sliding friction and toe resistance due to end bearing are modeled. Right? We don't adequately and correctly model the effect of a tapered deep foundation element. Traditionally, the deep foundation element is assumed to be wished in place, so each of these resistances starts from 0 magnitude, as I've shown you on these generic qualitative curves. Furthermore, it's traditionally been assumed the only source of load on the deep foundation element is external and is applied at the head of the deep foundation element. It's assumed, or at least implied, that the ground surrounding and beneath the deep foundation element is spatially and temporally fixed. I mean, we could see that. I mean, the supports of all these, if you will, soil springs along the shaft of the deep foundation element at the toe, these supports are assumed to be fixed in space, so that all vertical displacements of the overall deep foundation ground system reflect the deep foundation element moving downward or settling relative to the surrounding ground. And furthermore, the temperature of the deep foundation element and the ground do not change over time. So again, these are the basic assumptions that have been used since the TZQW methodology began to evolve in the 1960s. Now, in view of the current state of knowledge as we've discussed in this presentation, it's important to note that the different methods for evaluating the TZ and QW model spring stiffnesses, they're basically variations on a theme. And this is what separates the different specific methods within the overall TZQW methodology. Different methods have different ways for generating these force displacement springs for the shaft and the toe. Most of these different methods use models that are empirical to varying extents. Now, specifically, the spring stiffness models have historically neglected residual loads from installation, as the TZ and QW curves are assumed to start from the origin, that is, 0 load, 0 displacement, at the beginning of the solution algorithm, as I've already noted. Furthermore, the algorithm used for the overall TZQW problem solution has not been modified or adapted to consider down drag and the resulting drag loads from post-installation global settlement, or the thermomechanical behavior associated with newer technologies such as energy piles. And finally, deep foundation elements with a depth-wise variable perimeter, such as tapered deep foundation elements, are dealt with in a very approximate manner by using a stepwise variation in the perimeters of the artificial segments. But hopefully you can see by now, from what I've talked about in this presentation, that simply making the different segments different diameters is not the correct way to model, for example, a driven taper pile. All right, because it ignores the effect of wedging, the radial displacement that occurs with a tapered deep foundation element when it is loaded axially. So, as I said, this traditional model fails to capture the true behavior of tapered deep foundation elements, as the geotechnical mechanism of shaft resistance due to wedging is not modeled at all, not even approximately. Consequently, there's need to modify the traditional TZ and QW solution algorithm for several reasons. First of all, these relationships need to allow for initial non-zero forces simulating residual loads. As you'll see in the coming slides, this includes allowing for shaft forces to be both positive and negative in sign, and to be able to reverse direction in sign during the solution process. All right, because only positive shaft friction is modeled by the traditional TZ springs. The solution algorithm needs to include the effects of post-installation global settlement and the down drag and drag loads on a deep foundation element that result from this global settlement. Again, as will be seen, this involves a paradigm shift in the solution algorithm and its calculated outcomes. We also need to make sure the solution algorithm can include the effects of post-installation heating and cooling of the deep foundation element when it's functioning as an energy pile, in addition to providing axial load bearing. Again, as you'll be seeing, this involves another paradigm shift in the solution algorithm and its calculated outcomes. So the point I'm getting at here is we need to change quite a few things in order to be handle all the different load sources that we know that can exist. And finally, the geotechnical resistance of taper deep foundation elements needs to be modeled more accurately. So this is a pretty tall order. There's a lot of changes we need to make to this TZQW methodology. Now, the research that I've done to date has found that there is a promising method for developing TZ and QW relationships that is both simple enough to implement in routine design practice, yet I think is theoretically rigorous enough to make academicians happy so that they would use it in their academic research. The basic elements of the method I'm going to discuss were presented in a Federal Highway Administration sponsored research report that was published in 2006. You can find copies online and download it at no cost. And this results in a modified hyperbolic relationship for both the TZ and QW curves. This is achieved by using the core theoretical components of the Randolph-Roth problem. That is, the concentric cylinders model for shaft resistance, the rigid punch model for toe resistance, with shear modulus degradation using the Fahey-Carter model for both shaft and toe resistances as suggested by Paul Main. The multiple attractions of this proposed TZ-QW method or that it uses a sound, well-proven, theory-based approach to model how shear stresses and shear modulus vary as functions of load application and radial distance around a deep foundation element. As I said, the vast majority of TZ-QW curves are purely empirical, and by using a theory-based model, we can remove that empiricism. So we can eliminate the need for purely empirical methods for quantifying the TZ and QW spring stiffnesses. These empirical methods or models require data from instrument and static load tests combined with complex curve fitting algorithms, such as those proposed by Felinius and his co-workers. As I've said before, very few projects can have the budget and time to allow for instrumented pile load tests during the design phase in order to produce model parameters that could be used during the design phase. We need an analytical model that can hit the ground running and be used without doing a lot of expensive field testing. Another attraction is that the method I'm going to show you makes use of state of knowledge site characterization using seismic piezo-cone soundings and other in situ testing devices for measuring site-specific values of the small strain shear modulus, Gmax, using shear wave velocities. Such site characterization tools are nowadays universally available, so I feel that they are amenable to use in routine practice. We're not requiring anything that is out of the ordinary. And finally, the method I'm going to show you can readily be extended to include residual loads from installation. I've already done this, and I will show you later in this module the outcomes from this. And it also shows promise for further extension to include the effects of global settlement, thermomechanical behavior associated with energy piles, and the geotechnical resistant mechanism of wedging that occurs with taper deep foundation elements. Now, because although this proposed TZQW method was presented in the literature almost 20 years ago, I don't think it's widely known, no less used at present. So I'm going to summarize the basic theoretical elements in this presentation for the baseline wished in place case of a constant perimeter deep foundation element with no residual loads from installation, nor post-installation drag loads or thermomechanical effects, where both the shaft and toe resistance start from zero load. I'm then going to follow this up with a qualitative illustration of how this proposed method has been extended by me to include residual loads from installation. And I will include a worked example, a quantitative example of how I've extended this method for residual loads in the denouement segment at the end of this presentation module. I will also discuss potential future extensions to include modifications to incorporate down drag and drag loads from post-installation global settlements, incorporate thermomechanical effects from energy piles, and allow for the unique behavior of tapered deep foundation elements. I'll discuss these in an introductory preliminary manner because this is still work in progress research that I have going on. So I've not yet modified the method I'm going to show you for these other issues. This is still a research work in progress that I'll report on at some future later date. So let's start off by talking about the physical and mathematical model. You've seen this before. This is the free body diagram for the concentric cylinders model. I'm now going to expand on this to show you how we develop a usable solution. And again, the concentric cylinders model is just an infinite number of imaginary cylinders of linear elastic material that surround a vertical cylindrical void. And the starting point is we assume that we know the shear stress tau 0 or tau naught that is applied to the interface between the void and the innermost cylinder. And although the basic model was developed for a downward acting load from axial compression, being an elastic model, we can certainly use this for an upward load from uplift or tension. So you simply develop the partial differential equations, make some simplifying assumptions, and you get your end result to solve. Now, what makes this usable, of course, is that we turn this into a nonlinear elastic model by using a modulus degradation equation. And this is just a figure from the Federal Highway Research Report that shows you different modulus degradation models that they assumed, and focusing in on the Fahey-Carter model. And again, here's the equation of the Fahey-Carter model. And the attraction of the Fahey-Carter model is that starting from an initial value of G that is based on small strain theory, we get a behavior that much more closely mimics what actually occurs or has been found in research. This rapid degradation of modulus, then slowing down as failure is approached. So the solution for the baseline Wishton-Place case, let's go through this for different segments. These results all come from the Federal Highway Research Report. This is the typical settlement of a shaft spring. And you see the modulus degradation model has been embedded in here. And of course, from this, we can get a stiffness, spring stiffness. All right? We know displacement. We have an assumed load here, tau 0. So that gives us a spring stiffness. That gives us the overall curve that we need. And again, this just shows that the Fahey-Carter model, the red curve, shows you the forecast or calculated results that you get. This would be a linear elastic model. The blue dash curve would be a basic hyperbolic model. And this is the modified hyperbolic model of the Fahey-Carter model. And again, you can, this report includes some recommendations, as you could see, for F and G. If you wanted to, you could play around with these values. That will change the shape of this curve. But F equals 0.98 and G equal 0.25 is the basic recommendations, and those are the recommendations that I used in my work to date. Here's the solution for the toe resistance. They use a capital Z at the base. This is what we would call, I should note that what they call W sub S over here is what I call Z. What they call Z is what I call W. So this is, as I indicated to you earlier, in the TZQW methodology, there's a lot of inconsistency with notation, both the letters used, capital versus lowercase, things like that. So this just shows you the basic equation for the toe resistance. Again, for the toe, we're not using the concentric cylinders model, we're using this rigid punch model, but we're simply turning instead of having rigid plastic behavior, we now have nonlinear elastoplastic behavior. And this just shows you the resulting curve that you get compared to a conventional hyperbolic model and a elastic plastic model. So let's look qualitatively how this is applied to the baseline Wishton-Place case. And in this case, the equilibrium plane is at the ground surface. Here's the model for the shaft resistance. The core starts at 0, 0. And the model for the toe resistance also starts at 0, 0. And as we apply load to the head of the deep foundation element shaft and go up to the failure load QU, we will traverse the red curve in each of these two cases. Now to apply this to the residual load case, this is work that I've done to modify the model that was in the FHWA report. Now in this case, the equilibrium plane is below the ground surface, and we have initial negative and positive shear stresses as well as an initial toe load. So for shaft resistance, that means in the lower part of the deep foundation element, we're starting not from 0, but we have 0 displacement, but we have a finite magnitude of shear stress. So our curve is starting from this point here. Notice that the stiffness of the curve has to reflect what exists at this point. Now for the upper part of the deep foundation element shaft, for simplicity, what I assumed is that for negative shaft friction, this is just a mirror image of the positive shaft friction. This certainly seemed to me to be a reasonable assumption. Certainly this is a topic that can be researched in the future, but it seems to me reasonable if you have a constant perimeter deep foundation element that the negative shaft friction curve is just a mirror image of the positive shaft friction curve. And again, 0 displacement here has some initial negative shaft friction. Now, I do want to point out that for tapered deep foundation elements, the positive and negative shaft friction curves are likely not mirror images of each other. This is because the wedging and unwedging curves are most likely not going to be mirror images of each other. The wedging is probably a much stiffer curve than the unwedging curve. But clearly this is an area that needs to be researched. So now as we apply load to the head of the deep foundation element, up to the ultimate load, there is, of course, only ever one true shaft resistance. You start from 0 shaft resistance and you go up to some ultimate load. So there is only ever one true shaft resistance. However, in the lower part of the deep foundation element, where we start off with an initial positive shaft friction, we're going to measure a false shaft resistance. It's too small because we start from here and go to here, and we have neglected the shaft resistance that has already been mobilized. And I'm using the words false and true here to tie this into things that we saw much earlier in this presentation. When I showed you on some static load test curves, I labeled certain shaft resistances true and certain shaft resistances false. And I'm illustrating to you here why they're true and false. I've done this earlier in a qualitative manner. I'm now doing it again with the specific TZ QW curves of the model that I'm proposing. Similarly, for the region of negative shaft friction, I'm also going to measure a false shaft resistance. It's too large because they start from here, for negative, go to 0, and then have to traverse the entire positive shaft friction curve. So again, I'm just trying to illustrate to you, I've done this before and I'm doing it again a little bit different setting, why we have these so-called true and false shaft and toe resistances. I'll show you the toe resistance in a minute. So let's move on to the toe resistance. Now in the residual load case, we're going to start with some initial toe resistance. I showed you case histories previously, for example, that jack pile example, as well as the Holman Island piles had 40 or so, 50% toe resistance. Some of the driven tapered piles at Kennedy Airport had almost 100% mobilized toe resistance. So again, with toe resistance, we're starting with zero displacement, but with some initial value of toe resistance. And somewhere between 0.5 and 100% toe resistance is not uncommon, certainly for driven or jacked deep foundation elements. So now as we apply an axial load to the head of the deep foundation element up to the ultimate load, there is, of course, only ever one true toe resistance measured from zero toe resistance to an ultimate value. However, starting from an initial value, we're going to think we have a false, too small value of toe resistance. And again, this all ties into what I've showed you earlier in this presentation. This is why all the resistance forecasting methods that are in use at present tend to overpredict shaft resistance and underpredict toe resistance, because they were all calibrated or designed based on using static load test curves that were not corrected for residual load. So they use, as part of their calibration and design process, toe resistances that were measured that were too small and shaft resistances that were too large. Now, these visualizations, although generic and qualitative, again serve to illustrate why static load tests that are not corrected for residual loads due to deep foundation installation consistently overestimate the contribution of shaft resistance and underestimate the contribution of toe resistance. This was illustrated earlier in this presentation using case history data, and I've repeated it here in order to emphasize this important point. And again, this is some figures that I've shown you previously. This is for the monotube piles at Kennedy Airport. Looking at pile 3 as an example, this is the measured load. I think I have virtually no toe resistance, but all shaft resistance. But the true load is that I have a rather significant toe resistance, especially considering the toe diameter is only about 8 inches or 200 millimeters. This is the true resistance. I have a fairly significant toe resistance and less shaft resistance than I think I have from the measurements. And this is because the measured loads did not take into account the residual load from installation. And again, I've shown you these load test curves for the jack pile case history example of Felinius. This was the static load test as measured, and this is the true behavior for residual loads. Again, notice for the toe resistance, you're not starting from 0. You're starting from some initial value. And although not properly reflected here, the shaft resistance is actually starting from a negative value. So these visualizations also serve to illustrate and emphasize a point I made earlier in this presentation as to why virtually all static analysis methods for forecasting geotechnical resistance, both indirect and direct as well as hybrid, that were used in the past and are used in the present tend to forecast shaft resistances that are too large in magnitude and toe resistances that are too small in magnitude. Specifically, these analytical methods were either based on or calibrated with static load test data that were uncorrected for residual loads from installation that give false, that is, too large estimates of shaft resistance, and false, that is, too small estimates of toe resistance. As I've noted earlier, one of the several benefits of using the concentric cylinders model as a theoretical basis of a TZ-QW method is that it provides a sound theoretical framework for extensions beyond the baseline wished-in-place case. The most important of these extensions to include residual loads has already been discussed, and my research has shown that this extension is viable to use in both design practice and academic research at the present time. And I will illustrate this in the denouement segment at the end of this presentation module. Now, there are at least 3 additional extensions that merit investigation and development. One is a new solution to the concentric cylinders model that takes into account the radial displacements and changes in radial and tangential normal stresses that accompany externally applied axial loading of a tapered deep foundation element in both compression as well as tension or uplift. Second is modifications of the TZ-QW methodology to allow for the effects of post-installation global settlements on a deep foundation element. And a corollary subcase would be when there is post-installation heave, as can occur with expansive soils. However, I don't consider this expansive soil subcase in this presentation. And third, we have modification of the TZ-QW methodology to allow for the effects of post-installation thermomechanical behavior of a load-bearing deep foundation element that also functions as an energy pile. Each of these extensions is discussed further in the following slides. Let me first discuss the extension to tapered deep foundation elements, as driven tapered pile certainly is a topic near and dear to my heart. The concentric cylinders model, as traditionally formulated, solved, and used to date, implies that the deep foundation element has a depth-wise constant diameter, so that at any given depth, the change in radial displacement R, adjacent to the deep foundation element shaft, as a function of applied axial load on the deep foundation element is 0. This also implies that there are no changes to the radial normal stress and the tangential normal stress adjacent to the deep foundation element shaft as a function of applied axial load. However, these implications are no longer valid for a tapered deep foundation element, as there will be changes in radial displacement and therefore radial normal stress and tangential normal stress for both compressive and tensile externally applied axial loads due to wedging and under-wedging, respectively. Now, theoretical work to extend the concentric cylinders model to allow for these depth-wise variations of sigma r, and sigma theta as a function of the changes in vertical displacement u that occur as a result of externally applied axial load has been done by Mr. Regis Colasanti, PE, in consultation with me. That radial displacement and therefore these two stress components are function of the vertical displacement of a deep foundation element U simply makes use of the fact that they are geometrically related to the taper angle alpha of a deep foundation element. All right, so clearly as this taper deep foundation element either goes down under compressive load or up under uplift or tensile loading, there is going to be, in addition to axial displacement from geometry, there's going to be radial displacements as well. Now, these theoretical developments are currently a work in progress, but it's important to note that they only address the so-called phase 2 taper benefit that accrues when an installed taper deep foundation element is subjected to an externally applied axial load. They, of course, don't take into account the phase 1 taper benefit of installing the deep foundation element, especially by conventional impact driving or jacking. Considered next are extensions of the TZQW methodology to include post-installation global settlement and the thermomechanical behavior of energy piles. Both scenarios introduce significant analytical paradigm shifts and concomitant marked increases in analytical complexity for a TZQW analysis for several reasons. But first recall that the traditional TZQW methodology, including modifications that I've made to allow for residual loads from installation, is based on the assumption that axial displacements of a deep foundation element are solely the result of post-installation loads applied to the head of a deep foundation element. So it is the deep foundation element that dominates and, if you will, drives the problem. The ground adjacent to and below the deep foundation element is traditionally assumed to be temporally stationary and reactive only, so that both the mobilized geotechnical resistance at any depth along the deep foundation element shaft, as well as beneath the deep foundation element toe, are solely the result of relative displacement between the vertically displacing deep foundation element and spatially fixed ground. Okay, and with respect to the TZQW springs, I pointed out to you previously what that means is that the support for these springs is basically fixed in time and space. The shear strength of the soil around and beneath the deep foundation element is also assumed to be temporally fixed in magnitude, so that shear resistance along the deep foundation element shaft, as well as the bearing resistance beneath the deep foundation element toe, do not change over time. Temperature of the overall deep foundation ground system is not considered, and the traditional bottom-up solution is used because the TZQW methodology is crafted to produce a load settlement curve at the head of the deep foundation element that is mimicking the measured outcomes of a traditional static load test. So the point I'm making here is that in a traditional TZQW analysis, whether wished in place or accounting for residual loads, what we're looking for as the calculated outcomes are basically a load settlement curve at the head of the deep foundation element. We want to be able to mimic or replicate what occurs during a traditional static load test. So again, this is the wished in place baseline case. Notice the very important thing is that all these spring supports are fixed both in space and in time. The equilibrium plane starts at and remains at the ground surface. As we perform the TZQW analysis, the applied load starts at 0, goes up to the ultimate load. We are most interested in the settlement at the head of the deep foundation element in response to this load, and we only generate positive shaft friction along the entire shaft, as well as toe resistance. But again, very important to note that essentially the supports of all these springs remain fixed in time and in space. Now, what's different with the residual load case we talked about is that under zero load, the equilibrium plane is somewhere beneath the surface, and we have some combination of negative and positive shaft friction as well as initial toe resistance. But again, note that the support for all of these springs in the TZQW model are fixed both in space and in time. And again, what we're looking for is to apply a load at the head of the deep foundation element up to the ultimate load, to calculate the settlement of the head of the element of the deep foundation element as a function of applied load, and eventually we will turn all of the negative shaft friction into positive shaft friction, which is resistance under compressive load. So even when we start with residual load, still the desired outcome we're looking for is basically calculated results of settlement to the head of the deep foundation element as a function of applied load. So whether we start with the traditional Wishton-Place case or with a residual load case, the desired outcomes are always the same. And in our model, the supports for all of these springs do not change over time. The temperature does not change over time. The geotechnical resistance does not change over time. Let me first consider a TZQW analysis involving global settlement. And as it turns out, the tables are completely turned compared to a traditional analysis in several ways. First and foremost is that in this case it is the ground and not the deep foundation element that dominates and, if you will, drives the problem. This is because the ground around and possibly beneath the deep foundation element settles over time. And again, this can occur gradually over years or decades. It could occur suddenly over literally minutes in an earthquake. But they're for reasons that have nothing to do with the deep foundation element per se or the structure it supports, at least directly. Therefore, the ground is no longer a temporally fixed spatial frame of reference for the deep foundation element, as it is in a traditional TZQW analysis. And I think you can see, therefore, the problem it creates for us is that these spring supports are no longer fixed in time and space. As a result, the deep foundation element in the structure it supports to a very significant extent simply can go along for the ride. I showed you that photo earlier on of a driven pile that pulled completely out of the pile cap. I mean, there was no load on it, yet that pile settled rather substantially. In addition, the shear strength of the ground around and beneath the deep foundation element is no longer temporally constant, but is subject to change. Again, with the time frame and duration of that change varying widely. It could be years, decades, it could be minutes, depending on whether the ground displacements have static or dynamic causation. But as a result, the shaft and toe resistances of the deep foundation element are no longer temporally constant, but vary with time. And this variation needs to be taken into account. This role reversal between the deep foundation element and ground, that is, which component is driving the problem, if you will, means that the calculated outcomes from a TZQW analysis, in this case, are quite different compared to the traditional baseline case of no global settlement. So what we're looking for when we have global settlement as a calculated outcome is quite different. The primary desired outcome in this case is the settlement of the head of the deep foundation element as a function of time for the design life of the structure supported by the deep foundation element, so that the serviceability limit state of this structure can be assessed for, differential settlement, rotation perhaps. So for this assessment, the externally applied load on the deep foundation element is typically assumed to be constant in magnitude and equal to the unfactored design dead load. So again, in the traditional TZQW analysis, you're looking for a load settlement relationship at the head of the deep foundation element. It's completely different here. We're still looking for settlements, but now settlements as a function of time, not load, because we typically assume that the load is constant. Note that the externally applied live load is not considered, as live load application is accommodated by the negative shaft friction due to drag load reversing to positive shaft friction that provides geotechnical resistance necessary to counter the live load application with really minimal additional settlement. And I've showed you this now a couple times with both case histories as well as qualitatively. Now, also important are temporal variations in the magnitude and depth-wise distribution of axial compressive forces and the normal stresses within the deep foundation element shaft. These stresses are, of course, used to assess the structural ultimate limit state safety margin of the deep foundation element. It's also important to determine the depth of the equilibrium plane as it changes over time. As I pointed out to you several times, and as well as illustrated to you, the equilibrium plane is always a dynamic element, meaning that it can move up or down in the overall system as a function of time, load application, and other factors. So determining the depth of the equilibrium plane as it changes over time is also a mission critical component of the overall TZQW calculation process, as it defines the unique depth at which the global and deep foundation element settlements are equal in magnitude, and the axial force, but not necessarily the axial normal stress, in the deep foundation element shaft is at its maximum. Note that determination of the depth of the equilibrium plane at a given point in time is complicated by the fact that the geotechnical resistance of the deep foundation element is typically changing over time due to changes in the stress state around and beneath the deep foundation element. And we need to take these changes in stress and strength into account. Now, the stiffness of the deep foundation element end-bearing mechanism, as reflected in the QW mathematical relationship, plays a very significant role in determining whether the geotechnical serviceability limit state, as reflected in deep foundation element settlement, or the structural ultimate limit state, as reflected in the normal compressive stresses within the deep foundation element shaft, will be the more important design consideration in a specific application. As I pointed out to you previously, settlement and load in a deep foundation element are not going to be critical at the same time. Either one or the other is going to be the more critical. And it's also worth reiterating a point that I've made, that at no point is the geotechnical ultimate limit state ever a critical design consideration. The geotechnical ultimate limit state, it may change due to stress changes, but it's only going to increase in general. It's not going to decrease. But the important point I want to make here is that either the stress in the deep foundation element shaft or the settlement at the head of the deep foundation element is going to be the more critical in a application specific case. So to look at graphically what's going on now is, in the global settlement case, our load is assumed now to be constant, not variable, fixed at the dead load of the structure. What is important is that over time, the ground surface, which reflects in essentially the supports of some and possibly all of these springs, is settling over time. Now, I've only shown you some of the support settling. It is in principle possible that settlements may extend beneath the toe of the deep foundation element. This is just indicated to be representative. So a real paradigm shift here is that we can no longer count on the supports of these springs to be fixed in space. And that's what I'm emphasizing here. We're still most interested in settlement at the head of the deep foundation element, but now it's as a function of time under constant load, not as a function of load under constant time. And the equilibrium plane will no longer be at the ground surface. We'll have some combination of negative and positive shaft friction. And again, this equilibrium plane is a dynamic element. It is going to tend to go up and down over time as a function of global settlement, even under the constant load. Now, considering next the TZ-QW analysis, where in addition to providing axial load bearing, a deep foundation element functions as an energy pile that is part of a ground source heat pump system, the tables are again completely turned relative to the traditional analysis. Now we're back to the deep foundation element dominating and driving the problem, but in a very significant fundamental way that differs completely compared to the traditional TZ-QW analysis. And this is due to the inherent thermomechanical behavior of an energy pile. As I discussed in detail in the Phase 1 module of this presentation, this thermomechanical behavior occurs because the temperature within the energy pile shaft is constantly changing over time. And typically this is a cyclical pattern over a time frame of a calendar year that is related to the heating and cooling seasons in a temperate climate. These thermal changes cause volumetric changes of the deep foundation element shaft materials that result in cyclical axial displacements and axial forces being generated within the shaft for the entire length of the energy pile. There are also horizontal displacements of the energy pile shaft due to Poisson effect of the vertical forces that are generated. The calculated outcomes from a TZ-QW analysis of energy piles is really quite different compared to the traditional baseline case of no global settlement. With energy piles, the primary desired outcomes are vertical displacements and vertical forces at the head of the energy pile as a function of time for the design life of the structure supported by the energy piles, so that the serviceability limit state of that structure can be assessed. Although, as I've noted previously, it is typically adequate to analyze just the peak heating in season and peak cooling season in order to bracket the problem. Note that a unique aspect of energy pile applications is that vertical displacements at the head of the energy pile are cyclically up and down as opposed to being monotonically in one direction, usually settlement, as in all the prior cases. And note also that in energy pile applications, the vertical load at the head of the energy pile is neither known beforehand nor can it be assumed, as it is, at least in principle, part of the problem solution. Although, as I've noted earlier, certainly as preliminary design, we could bracket the problem by looking at the limiting cases of no restraint and full restraint at the head of the energy pile. Also important are temporal variations in the depth-wise magnitude of axial compressive forces and normal stresses within the energy pile shaft in order to assess the structural ultimate limit state safety margin. However, it's worth noting and repeating that at no point is the geotechnical ultimate limit state ever a critical design consideration. The vertical stiffnesses at the head and toe of the energy pile play an outsized role in determining the relative proportion of thermomechanical vertical forces versus vertical displacements that occur in a specific energy pile application. The QW relationship defining the toe and bearing stiffness can be determined in a straightforward manner, as I discussed previously in this presentation segment. But determining the stiffness at the head of the energy pile on a project-specific basis can be analytically challenging and time-consuming, as I discussed in the Phase 1 presentation module. Also, as I discussed earlier in the Phase 1 module, in practice it may be adequate to simply analyze both the idealized free end and fixed end limiting conditions at the head of an energy pile to bracket the problem, and only analyze the exact project-specific intermediate stiffness case if necessary to determine the vertical forces and displacements more exactly. Determining the depth of the equilibrium plane remains an important part of the overall energy pile problem solution. So let's look at things graphically as we've done before with the other cases. And I want to emphasize that I'm only illustrating the thermomechanical behaviors here. These behaviors have to be combined with and superimposed on the geostructural behaviors, including residual loads, global settlements, if any. So in the peak heating season, notice that in addition to the model, we have a spring stiffness at the top of the uppermost element in our TZQW model. And this represents the interaction, the structural interaction with the overlying structure. Now in the peak heating season, the heat flow is outward out of the ground. Again, the energy pile is being used as a conduit or load transfer element to bring the heat from the ground to the overlying structure. So the energy pile is going to cool down and tend to contract. This is the equilibrium plane with the shear stresses along the energy pile shaft that will develop in response to this contraction. And notice that the negative shaft friction is in the lower part of the energy pile, which is different from all the cases we've looked at so far. You're going to get a contractive force and upward movement, tendency for upward movement at the toe, and a contractive force and tendency for settlement at the head of the energy pile. Now in the peak cooling season, again, we have a spring stiffness at the top of the energy pile to model. Heat flow now is into the ground, from the structure into the ground via the energy pile. As a result, the energy pile is going to heat up and going to tend to expand. And this is our equilibrium plane and the shaft frictions that will tend to develop. Notice a complete reversal of shaft frictions compared to the peak heating season case. Now, in the peak cooling season, the tendency is for compressive forces and settlements at the toe, and compressive forces and heave at the head of the energy pile. And again, the proportion between force and displacement is going to depend on the spring stiffnesses at the head and toe of the energy pile, and there will also depend on the stiffness of the ground, because some of this force displacement tendency is going to be absorbed via shaft friction in the ground. Now, extending the TZQW method that is based on the concentric cylinders model to take into account the radial displacements and changes in radial and tangential normal stresses that accompany externally applied axial loading of a taper deep foundation element in both compression and tension uplift, allow for the effects of post-installation global settlement, allow for the effects of thermomechanical behavior of a load-bearing deep foundation element that also functions as an energy pile. Each of these topics is currently a work in progress that I have in collaboration with Mr. Colasanti. So at this point, there are no results that I could show you. This is very much a work in progress. A large part of the work in progress reflects the fact that we now have to come up with a different solution methodology. The bottom-up solution methodology that has been used traditionally with the TZQW methodology really is not appropriate for use for any of these cases. Now, before leaving the topic of single deep foundation element behavior, there's one more topic I want to talk about, and that is the Niazi load settlement method. The doctoral research of Professor Fawad Niazi that was conducted earlier in this century at Georgia Tech under the supervision of Professor Paul Main resulted in yet another analytical method that incorporates the concentric cylinders model. What I call the Niazi load settlement method is a clever rearrangement of the Randolph-Roth problem solution that uses a site-specific profile of the small strain shear modulus Gmax as obtained from shear wave velocities in a seismic piezo-cone sounding, a database of empirical relationships created using load settlement data from static load tests, and uses these to generate a load settlement curve for an arbitrary deep foundation element of a specific type and geometry. Niazi's database was created for a wide variety of driven, jacked, and drilled deep foundation elements of depth-wise constant perimeter. And I found from my personal research that similar databases can easily be created for other types of deep foundation elements not included in Niazi's original database. For example, deep foundation elements that are torqued in the ground, as necessary calculations can be performed using spreadsheet software. So what I'm getting at is basically you can create your own database to use the Niazi load settlement method. It's just a rather easy set of calculations you could do with any spreadsheet software. And I extended the database to include driven tapered piles at Kennedy Airport. Now, basically, the way that Niazi's method works is that you process load settlement data from static load tests. And what Niazi did, this just shows all the load test data together. And then he broke them down into load test data sorted by different types of deep foundation elements, driven, jacked, drilled, etc. So this is the sort of relationship that if you had some site-specific data for a given type of deep foundation element, you would create a relationship that would look like this. Ideally, they would define a line in log-log space. And from this, you get an empirical equation of the shear modulus degradation. So what's an interesting kind of turnaround with the Niazi load settlement method is instead of modeling the shear modulus degradation using, say, the Fahey-Carter model, that you basically experimentally determine the shear modulus degradation based on site-specific load test data. And that's what I'm indicating to you here. So anybody could do this for any site, any type of deep foundation elements. You could run a series of static load tests, process the data, and generate your own site-specific shear modulus degradation equation of this form. You'd also need to do, say, a seismic piezo-cone sounding or obtain shear wave velocities that you could process into Gmax or small strain shear modulus. And that's what we're showing here. This just shows Gmax, the small strain shear modulus, as determined from shear wave velocity measured in the seismic piezo-cone sounding, and you do a site-specific linear fit to the data. And then you take your Randolph Roth problem solution equation I showed you previously. This is the compressible pile solution. And your operative shear modulus is going to come from your site-specific degradation equation you've determined. And you simply assume different magnitudes of load and calculate different magnitudes of settlement. And you're going to create this simulated load settlement curve. And again, this requires nothing more than a spreadsheet solution. So the idea is that what you could do on a project-specific basis is you could develop your own site-specific relationship and be able to now use this to generate what-if load settlement curves for, say, at that site, deep foundation elements of, let's say, different embedded lengths, things like that. You could do all sorts of what-if games. You could generate a series of load settlement curves for deep foundation elements of a certain type of different embedded lengths. So this is a very interesting tool that I found to play around with. I think it still needs some work, but it certainly is a nice indication of where I think things are headed in the future, of basically relating the load settlement behavior of deep foundation element to ground stiffness as opposed to ground strength as we've done traditionally. And that's the main reason I wanted to show you this method, was to show you that we could look at the load settlement behavior of a deep foundation element strictly from the perspective of ground stiffness. Notice there's no strength issues here. Okay, this is just the stiffness of the shear stiffness of the ground. So we could look at load settlement behavior strictly as a function of ground stiffness as opposed to what we've been doing now for a couple hundred years of looking at it from a shear strength perspective. Now, I've used the NIASE load settlement method for some years now as part of my research, and I've developed some observations from this. The method inherently incorporates the effect of residual loads from installation in the deep foundation ground system stiffness, although NIASE did not note this fact in any of the publications that I've read that discuss this method. Unfortunately, the calculated method parameters, again, you want to determine a site-specific empirical equation for shear modulus degradation. Unfortunately, the method parameters are very sensitive to the quality, and by that I mean the precision and accuracy of the static load test settlement, load settlement data used to create a database for the method. Specifically, because of the logarithmic plotting that are used to interpret load test data to produce the method parameters, the load test data under relatively low load levels, where the magnitudes of deep foundation element settlement are typically relatively small in magnitude, play an inordinate role in the interpreted data. So one of the things is that if you're going to use this method, you've got to actually take most of your data should be under very low load levels. And that just is a artifact of the logarithmic plotting that are used to develop the method parameters. So the load settlement response under very small load, relatively small load levels is very important. And those settlements have to be as accurate and precise as you can make them, because they're going to really determine the linearity of the data fit that you're trying to make. Now, at the present time, my feeling is that this method is best used as a preliminary designs tool, especially on larger projects where a site-specific database can be created using site and project-specific data for ground stiffness, type of deep foundation elements, and nothing more than a spreadsheet solution to produce the required parameters. As I said, I think that it's an interesting method, but it's got a ways to go before we develop a lot of confidence in its calculated outcomes. Well, I now want to move on to say a bit about group behavior. As I've noted previously, although deep foundation elements are installed individually, they're typically used in groups or clusters, especially in terrestrial applications, with each individual deep foundation element connected to a common structural element, and that structural element functions as a load distribution element between the deep foundation elements and the structure that they support. Now, historically and most commonly, this structural element, this load transfer element, is what we call a pile cap, although piled rafts have become increasingly common in recent decades. Therefore, in design practice, it is essential to correctly scale up the concepts of deep foundation element design based primarily on the geotechnical serviceability limit state that apply to a single deep foundation element to group behavior. Now, of relevance to this discussion is that the structural element, the pile cap or the bat or the raft, that connects the deep foundation elements in a group can exhibit a substantial range in horizontal dimensions, and therefore how many deep foundation elements are connected together. And more importantly, this affects the flexural stiffness of the structural element. Now, deep foundation group behavior is discussed in a comprehensive, theoretically rigorous manner in Fellinius's so-called Red Book, as I've noted previously. This textbook was first published, as best as I can tell, in 1996 in a traditional hard copy format. Had a red cover, hence the name, but for many years now has been available digitally online in what Fellinius calls an electronic edition, and he usually updates that annually. And as I've noted previously, it was updated in January 2025. Now, because the Red Book is now universally available at no cost and represents a detailed state of knowledge discussion of deep foundation group behavior, only a very brief overview and summary of group behavior is presented in this presentation. And I refer you to Fellinius's Red Book for a more thorough discussion of this subject. Now, as I've noted earlier in this presentation, Fellinius divides deep foundation group behavior into two categories, narrow and wide. He defines a narrow group as having no more than 4 rows of deep foundation elements. Narrow groups are assumed to have a pile cap that is flexurally rigid, so that all the deep foundation elements in the group settle the same amount, at least at the head, with the overall group behavior broadly similar to that of a single deep foundation element, including under conditions where post-installation global settlements can develop. However, for narrow groups, the potential for the footprint of the group at toe level, forming what Fellinius terms an equivalent raft that stresses the ground beneath the toes of the deep foundation element, much more than that of an individual deep foundation element, and sufficiently to cause a significant component of group settlement, needs to be evaluated. So when you perform a TZQW analysis, for example, yes, you get a reaction at the toe, but that is just for a single deep foundation element. What Fellinius is saying is that when you have a narrow group, the effect of all the toes of the deep foundation elements can form what he calls an equivalent raft and can stress the ground beneath the toe sufficiently to cause a magnitude of settlement that needs to be taken into consideration. Now, the behavior of wide groups is much more complex and nowadays includes hybrid applications such as piled rafts and piled pads. A significant behavioral characteristic of wide groups is that the depth-wise axial load transfer behavior along a deep foundation element shaft can vary substantially between the deep foundation elements within the center of a group and the deep foundation elements around the periphery of the group. Very, very different behavior in terms of axial load transfer. In fact, for the piles in the center of the group, the the TZQW results are basically of a single deep foundation element are no longer applicable. In addition, the flexural rigidity of the structural member connecting the heads of all the deep foundation elements, such as the piled raft, can no longer be assumed to be rigid, with the result that differential settlement can occur across a group. And this is especially true of piled rafts. So collectively, these behaviors mean that the load settlement behavior wide group cannot be correctly analyzed by simply scaling up the behavior of a single deep foundation element, as you can reasonably do for narrow groups to a significant extent. When it comes to wide groups, they're very individual, and you need to look at things on a much more individual basis. And again, I would refer you to the extensive discussion of this in Fellinius's textbook. Well, that now brings us to the final segment of this Phase 2 presentation module, a denouement where I want to tie together all the things I've talked about. And as you will see, a feature of this denouement will be, I will show you some calculated outcomes from this TZQW method that I discussed at length in this module, and I will compare the calculated outcomes to some pile load test results from Kennedy Airport. Well, we've certainly covered a lot of ground in this presentation in general, and this Phase 2 module in particular. So let's step back for a second and just kind of sum things up to see where we are. I've showed you that defining the load settlement behavior of a single deep foundation element is the fundamental cornerstone element of deep foundation element design for axial loading that is based on the geotechnical serviceability limit state, that is, the axial displacements of the deep foundation element. I've showed you that the TZQW analytical methodology is a useful tool for this purpose. And I showed you that the TZQW analytical methodology can readily be modified to account for residual loads from installation, which is now recognized as being mission critical, especially for certain types of deep foundation elements such as driven and jack piles. The TZQW analytical methodology also shows promise for use in applications where global settlements, as well as the thermomechanical behavior of energy piles, needs to be considered. I showed you that the concentric cylinders model from the theory of elasticity provides fundamental theory-based insight into the overall behavior of a deep foundation element ground system under axial loading, and the key role played by the shear behavior and shear stiffness of the ground around a deep foundation element subjected to axial loading. This model has parameters that can readily be quantified using state-of-practice site characterization based on pisocone and seismic pisocone soundings. This model can readily be modified to accommodate empirical modulus degradation models in order to model nonlinear soil behavior. This model can readily be implemented into the TZQW analytical methodology. This model can readily accommodate residual loads from deep foundation installation. And this model has potential for theoretical extension to explicitly consider the behavior of taper deep foundation elements, global settlements, and the thermomechanical aspects of energy piles. So I think it's pretty clear that the concentric cylinders model, if you will, checks all the boxes of what is required of a TZQW analytical method for use in designing deep foundation elements based on the geotechnical serviceability limit state. I'm going to illustrate these combined outcomes using a case history. Note that the results that I present are intended to serve only as a proof of concept for what is possible using the information contained in this presentation. So the solution was made using generic spreadsheet software. Certainly with some time, somebody I'm sure could come up with a more elegant solution, especially if you used application-specific software. The case history that I selected for use here is one that I've presented in several earlier publications. It involves a monotube type tapered seal pipe pile, specific nomenclature 3N3 J8x14, with a post-installation poured-in-place Portland cement concrete core that was installed at Kennedy Airport in New York City towards the end of the 20th century. This pile, which was designated Pile P5A by the Port Authority of New York and New Jersey, was installed as part of a design phase field test program developed by the airport's operator, the Port Authority of New York and New Jersey, to evaluate deep foundation alternatives and their load-bearing capabilities in axial compression for a proposed large-scale renovation project at Kennedy Airport. Now, in the interest of full disclosure, as I've indicated before, I did start my professional career with the Port Authority in New York in the early 1970s. However, by the time this work was done in the late 1980s, I had moved on to consulting practice full-time and, in fact, had just started working full-time in academia. However, I still had some good contacts, some friends at the Port Authority, and they generously gave me pile load test data as well as subsurface site characterization data for use in my research when I was in academia. The actual project for which Pile P5A and others were installed did not go ahead at that time, although there have been subsequently several major renovation projects at Kennedy Airport, primarily in what is known as the central terminal area. And in fact, there is another major renovation project in the central terminal area going on at the present time, being August 2025 when this is being narrated. This field test program had several components and desired outcomes that were unique and drastically pushed the envelope for the deep foundation element state of practice at Kennedy Airport at the time. And in a few slides, I'll explain what had happened that was incorporated into this test program. But specifically, the alternatives that were considered in the 1980s had considerably greater depths of embedment and considerably larger geotechnical ultimate limit state magnitudes compared to the timber piles that had been used historically up to that point in time at Kennedy Airport. As I've indicated previously, from when the airport was first constructed in the 1940s until well into the 1970s, timber piles were the deep foundation element of choice at Kennedy Airport, installed, of course, by impact driving. But there were things that developed in the 1980s, I'll explain in a minute, that caused a real paradigm shift in terms of foundation design. This 1980s field test program was also the first to make use of extensive cone penetrometer soundings at Kennedy Airport, and probably one of the first, if not the first, large-scale uses of the cone penetrometer in the New York City metropolitan area. Now, initially in the 1980s, they used just a cone that measured tip resistance and sleeve friction, but soon switched to piezo cones that also measured pore pressure at the common U2 shoulder location behind the cone tip. In the 21st century, seismic piezo cones have now become quite common at Kennedy Airport. I'm going to show you a couple graphics that illustrate the depth of embedment of pile P5A, first supposed on a typical geologic profile for Kennedy Airport that I showed you previously. This is a very typical cone penetrometer sounding in the central terminal area. The raw data were provided to me. I did this interpretation of the yield stress ratio and KO. And again, we have a Holocene fill stratum. This is hydraulic sand fill that was placed in the 1940s when the initial airport was constructed. We have a Holocene organic stratum. predominantly organic clay with some peat. And then we have the upper glacial aquifer, which we now divide into individual strata. So these are two Pleistocene strata. They are both coarse grained, but they do have different gradations and different soil parameters and properties. Now, pile P5A, the nomenclature used in the monotube product line was 3N, 3J, 8x14. Let's define what that means. First of all, this pile used what was called a J taper section. And the monotube pile line used to have three taper angles that were available, F, J, and Y. J was the intermediate, had a taper angle of 0.57, which is about twice the taper angle of the typical timber piles that were used at Kennedy Airport at the time. This taper section was 25 feet long, and the toe of the pile was at a depth of 64 feet, so about not quite 20 meters, about 19.5 meters below the surface. The tip diameter was 8 inches, 203 millimeters. The top of the taper section, 14-inch diameter, 356 millimeters. So that's what the J 8x14 stands for. There was a constant diameter, what's called a type N extension. So the head of the pile also was 14 inches, and that's what the N here stands for. And what the 3 means, this is the gauge of the cold form steel. 3N means that the constant diameter extension was 3 gauge. 3J means that the tapered section was also 3 gauge. And this was the thickest steel that was available in the monotube product line, about 1/4 of an inch thick, 6 millimeters thick. Because the monotube pile sections were cold formed, there were real limitations on how thick the steel could be. That was one of the things that the later taper tube pile introduced. The taper tube is made out of hot rolled steel sheet, so you can go to thicker wall thicknesses as desired. This was the shear modulus, small strain shear modulus profile, Gmax, that I interpreted based on seismic Pisa cone data that was taken closest to the P5A location based on shear wave velocities. And here's the pile superimposed on that small strain shear modulus profile. These are the same scales on both plots. Now, to talk a little bit more about this 1980s test program and why it was such a paradigm shift at the time. The deep foundation elements that were installed as part of this late 20th century field test program that included pile P5A really marked a tectonic paradigm shift at the time for geotechnical design in general and deep foundation design in particular at Kennedy Airport. As I noted earlier in this presentation, for the first 4 decades of the existence of Kennedy Airport, from the 1940s to the 1980s, the deep foundation elements used were primarily timber piles installed by conventional impact driving, with a relatively modest embedment in the Pleistocene sand bearing stratum. So this just shows a typical timber pile, actually through the 1980s. Although there was not a lot of work done between the 1970s and 1980s. And as you can see, very modest embedments, 5 to 10 feet, 1.5 to 3 meter embedment into the Pleistocene sand stratum. And this was possible because of the high natural overconsolidation of this upper part of the stratum and the concomitant high KO values. And as we've seen throughout this presentation, KO affects not only shaft resistance, but toe resistance as well. And as I've mentioned previously, the timber piles installed at Kennedy Airport, certainly in the 1970s that I'm most familiar with, typically had tip diameters of about 8 inches, so about 200 millimeters. So they had a tip diameter that was the same as the P5A monotube pile I noted previously. But again, these piles had about, although they were continuously tapered, they had about half the taper angle of the Type J monotube taper. However, in the latter decades of the 20th century, there was a complete rethinking of seismicity and the seismic potential in the entire New York City metropolitan area. The seismic potential had always been there, but it really was only came to life and was researched and accepted in the latter decades of the 20th century. And for the first time, for example, the New York City Building Code incorporated a seismic design requirement. And I showed you this slide previously. This is based on research done at Lamont Doherty Earth Observatory of Columbia University, showing known seismic events going back to the colonial era in the 17th century in the New York City region. And again, here's Kennedy Airport. By the way, if I can digress, just in the couple of days that I have been narrating this presentation, there have been 2 seismic events. Very rare to have 2 events so close together, literally within about 2-3 days of each other. Both were epicentered right around this area in northeastern New Jersey. The first one had a magnitude of 3.0, and the second one had a magnitude of 2.7. And they're both located in this area. The second one was a bit closer to me. I live in this general area here. That's where my home office is, that I'm sitting here right now making this narration. I actually felt the second one more than the first one, although I heard the first one more than the second one. The first one happened about 10 o'clock at night, so it was quiet outside, so I actually could hear the rumbling of the earthquake. But the second one happened right around noontime on a weekday. A little bit noisier out, but I certainly felt it more. Actually, it was a bit closer to me. But anyway, it was interesting because, as you could see, this area in northeastern New Jersey is actually one of the less seismic areas. It's not close to this major Ramapo fault where they had a fairly significant event a little bit more than a year ago. And actually, there had been earlier this summer, there had been a cluster of small earthquakes along the Ramapo fault, kind of roughly in this area here. But anyway, I thought it was just kind of an interesting coincidence that these events happened, these small events happened while I was making this narration. But it is a reminder that there is certainly a modest seismic potential in the New York City area, and and given the fact that many parts of the New York City area, including Kennedy Airport, have very classic seismic liquefaction potential, these are things that we do need to take into account. In any event, this seismic reassessment of the late 20th century resulted in significant changes in foundation design at Kennedy Airport that resulted in a requirement for much deeper embedment of deep foundation elements within the glacial stratum due to liquefaction potential within the shallowest portions of the upper glacial aquifer. And usually all of the analyses I've seen, as well as analyses I've done independently, suggest that the greatest liquefaction potential is right here at the uppermost portion of the glacial aquifer of the Pleistocene stratum, just below the contact with the organics. And you can see the drop off in the tip resistance, actually in the yield stress ratio, and also in the tip resistance of the cone. So the greatest concern really is liquefaction here, which is, as you can see, this is really the area where the timber piles fetched up. So because of that, The use of fairly short timber piles like this was no longer allowed. And just to show you things by comparison, this is pile P5A, which has about a 45-foot, about 13.5 meter embedment into the Pleistocene bearing stratum. So this just shows you, now the diameters are not to scale, but the depths are to scale. This shows you P5A, then a pile P5A that I'm talking about here, compared to the timber piles that were used pretty much from the 1940s through the early 1980s at Kennedy Airport. And I could tell you that all of the driven piles that have been installed at Kennedy Airport from the late 20th century and as well as into this early years of the 21st century, they typically bear somewhere with tips down in really kind of in this range down here. Very, very common. Pile P5A was load tested after installation in a conventional incremental static load test using deadweight reaction, with the desired goal of defining the geotechnical ultimate limit state of this pile. Consequently, it was loaded to over 2 inches, 50 millimeters of settlement of the pile head, as opposed to simply loading the pile to some arbitrary limit such as double design, as is typically done during production pile driving. This settlement magnitude allowed for an adequate range of load settlement behavior to be measured and the geotechnical ultimate limit state to be reached for all practical purposes, which was, of course, very useful for my research. And this because the range of load settlement behavior provided an excellent basis for comparison with both geotechnical ultimate limit state analytical methods that I used, as well as the TZQW analyses that I performed in the past, as well as for this presentation that I will show you shortly. Now, there were other essentially identical monotube piles installed at Kennedy Airport during the same late 20th century time frame. You know, we're talking late 1980s, early 1990s. And some of these were fully instrumented along the pile shaft prior to static load testing. This allowed, and I show you some of those outcomes actually, remember the pile 2, pile 3 from the Felinius et al. Paper that I showed you earlier in this presentation. They were from that early 1990s time frame. So these instrumented pile load tests on monotube piles allowed for post-installation analytical assessment of residual loads from installation using techniques presented by Felinius in his various publications. In fact, Felinius was a consultant to the engineering department of the Port Authority of New York and New Jersey for these instrumented test piles on monotube piles in the early 1990s, which explains why he's the senior author of that paper. The following slides illustrate how the analytical methods for calculating the geotechnical ultimate limit state and for performing a TZQW analysis that were illustrated in this presentation, as well as related publications and presentations by me, can be combined to forecast the following outcomes for pile P5A. Settlement of the head and toe, as well as elastic compression of the shaft as a function of externally applied load. This simulates the actual static load test that was performed on pile P5A, so the calculated head settlements can be directly compared to the measured data. The depth-wise variation of vertical forces within the pile shaft as a function of applied load. The depth-wise development of geotechnical resistance is simply a mirror image of these shaft loads. The mobilization of total shaft and toe resistance, geotechnical resistances, as a function of applied settlement. And I'm going to present these results for both the baseline case of no residual load from installation, as well as with an assumed residual load from installation. Now, although residual load was not estimated for pile P5A explicitly, I just did a crude estimation using results obtained on essentially identical monotube piles at Kennedy Airport that were fully instrumented prior to static load testing. The two monotube piles that Felinius et al. Talk about really they were the same dimensions, and they were almost exactly to the same depth of embedment as pile P5A. Again, keep in mind that my goal here is really proof of concept. Okay, I'm not looking for something that's going to be used as commercial software. I really was interested in proof of concept at this point. So let's talk about the TZQW analysis for pile P5A for the baseline case of no residual loads. And I'm first going to show you results that mimic the static load test. Here I'm plotting the externally applied load at the head of the pile, kilonewtons. Here I'm going to be plotting the settlement and shaft compression both in millimeters. Okay, so these square orange symbols represent the measure data. The reason for duplicate data at some load levels was at the time the Port Authority Engineering Department was a big fan of not only did they run unload-reload loops at times, but what they would do is that at certain load levels, at higher load levels, they would do an extended hold to see what creep settlement happened under that sustained load. So that's why you see double values at some of these points. Some of them represent, I don't show you the curves themselves just to keep things clean without cluttering up the graph. So that's why you see some double values. Some of these represent extended hold times, some of these represent unload-reload loops. And again, this test was carried out to over 2 inches, 50 millimeters of settlement. So I think for all intents and purposes, it did reach the geotechnical ultimate limit state. And you see here I'm showing you the three curves. One is the head settlement, toe settlement, and elastic compression. Now, at the same time, this is now going to be an animation. So as you'll see the simulated results in an animation from my TZQW analysis. At the same time, you'll be seeing a graph that shows you the axial load distribution in kilonewtons as a function of depth. Now, this is the ultimate geotechnical ultimate resistance that I calculated, and for this I used the modified Nordland or Horvath method that I've developed over the last 25 plus years. I started developing this in the late 1990s. So this comes from a theoretical calculation that I did, and the green curve that you see will be the results from the TZQW analysis that I did using spreadsheet software. Again, I used Excel, but you could use any spreadsheet you want. This dashed line just shows you where the transition is from constant diameter to the tapered section, and this just shows you the toe of the pile. Okay, so here's the pile, the constant diameter section and the tapered section. And again, you'll be seeing you'll see this curve will stay fixed in space. You'll see this curve slowly march up and eventually join this curve during the simulation. So in the animation I'll show you on the next slide, there's going to be two things going on at the same time. You're going to be seeing the head, toe, and elastic compression curves start at 0 and work their way across here and then down here. And you'll see this green curve march across the graph as load is mobilized as a function of applied load at the head of this pile. Okay, so let me begin the animation. Before I do that, let me just point out that the geotechnical ultimate resistance of this pile was about 2250 kilonewtons. So about 500 kips, and in local colloquial usage in the New York City area, we would call this a 125-ton pile. Okay, so this assumes a typical safety factor of 2 against geotechnical failure. So this has an ultimate resistance of 500 kips or 250 tons. So this would be considered a 125-ton pile. And just for comparison, just to show you what a tectonic change this was from what had been done from the 1940s to the early 1980s at Kennedy Airport. Again, the state of practice at Kennedy Airport by the early 1980s was to use a so-called 30-ton timber pile. And this is the ultimate geotechnical resistance of a so-called 30-ton timber pile at Kennedy Airport. Ultimate resistance of 120 kips, or about 530 kilonewtons. So about 1/4 of this pile. So this is what I was saying. Not only were the piles from this late 1980s test program substantially deeper than piles had been at Kennedy Airport at the time, the designers were looking for ultimate geotechnical resistances for these piles that were about 4 times greater than what had been used historically up to that point in time. So this was, that's why I said, this was a real tectonic change in the foundation design for Kennedy Airport in the 1980s. So let me begin the simulation now. Again, starting from 0 shaft and toe resistances, we kind of build up the depth-wise resistance. Here we've maxed out all the shaft resistance with relatively small displacements, and now we're maxing out the toe resistance, which takes much greater displacement to mobilize. That's why you see this fairly sharp break in the load settlement curve. So again, what we've seen here is that shaft resistance, which only requires a fraction of an inch, a few millimeters of displacement to mobilize. Shaft resistance mobilizes with relatively modest settlements. And once we max out the shaft resistance, to mobilize the remaining toe resistance requires substantially more displacement. That's why we have this sharp kink in the load settlement curve. This is at the head, this is at the toe, and this is the elastic compression. So we see at the maximum, the elastic compression is calculated to be about 10 millimeters, so it's about 4/10 of an inch. And again, for the baseline no residual load case, we start at 0 and end at the theoretical resistance. What I next want to show you, still for the baseline no residual load case, I want to show you how the geotechnical resistance develops as a function of settlement at the head of the pile. And again, I'm going to be, here's the measured resistance at the head of the pile, total resistance. I'm going to be showing you 3 curves. Total resistance, shaft resistance, and toe resistance. And again, I will show you how this develops as a function of axial load developing as a function of depth. So what you will see is that the shaft resistance maxes out fairly quickly with modest settlements, and then it takes a lot more settlement to max out the toe resistance. And again, this is the calculated ultimate resistance we're looking for. Around 2250 kilonewtons, around 500 kips. Again, what locally in New York City would be considered a 125-ton pile. So let me begin the animation. All right, again, you see very little toe resistance mobilized. Just about all the resistance is shaft resistance up to this point. Toe resistance is very slow to mobilize. Now I've maxed out shaft resistance, and now any additional resistance comes from toe resistance, requiring much greater settlements. Until after about over 2 inches, 50 millimeters of displacement, I've, for all intents and purposes, have reached the geotechnical ultimate resistance. So you see the dashed red line, which is the total resistance, as it did in the prior graphics. It matches the measured reasonably well, although it shows a somewhat softer response than what was measured. And we will see why in a minute. These calculated results were textbook perfect, but unfortunately all wrong. And here's why. From the instrumented monotube test piles at Kennedy that were driven around the same time frame, and again, these piles were identical, 3N, 3J 8x14 piles, very similar embedments. Remember, the pile P5A was embedded about 19.5 meters. This pile is embedded 20, and this was about 20.5 meters. So almost identical embedments, identical piles were used for the instrumented load tests that were done just a couple of years after pile P5A was installed. And the reason the results I just showed you would look very nice but were all wrong is because they did not include the residual loads, which were quite substantial, as we've discussed now in earlier parts of this presentation, especially the fact that almost 100% of the toe resistance was mobilized as the result of installation. So now I want to show you the simulations that I did, the TZQW analysis of pile P5A for residual loads. And again, this was the result of modifications that I made to the analytical methodology that was shown in that Federal Highway report based on the concentric cylinders model. So this was the assumed initial conditions I just showed you without the residual loads. Okay. And this is the assumptions I made for initial conditions with the residual loads. Now, the residual load distribution I used was very simplistic. And again, my goal here was really proof of concept. I was not looking to match the exact residual load distribution in pile P5A. I used an approximation for simplicity, just to, again, as you know, when we do research, we do things in steps and stages. So I was interested to see if my modifications to the TZQW method for residual loads, if they were on the right track or not. So now when I show you in the animations, the simulations I'll show you in a minute, you're going to be looking at a couple things. For the ones I just showed you, this red curve remained static, and we saw the green curve kind of march across the screen here. Well, in the animations I'm going to show you next, the red curve, which is the ultimate resistance, that hasn't changed, of course. Residual load does not change the ultimate geotechnical resistance. We've said that a million times, so now I'll make it 1,000,001. The red curve is not going to change. The green curve will again start from 0. This is our applied load, right? The green curve is the applied load. However, the blue curve is the actual load. Okay, so you'll see this green curve move across the screen, and you'll also see this blue curve move across the screen. So this is, you're going to see a little bit more complicated animation. Now again, this is the assumed residual load distribution, which is also the actual or true load distribution that I assume for pile P5A. And you can see that this is it's simplistic, but it is a reasonable approximation of the residual load distributions that Felinius and his colleagues at the Port Authority Engineering Department observed in the two instrumented monotube piles a few years later. So this blue curve is meant to be an approximation of the blue curve for these otherwise identical monotube piles that were fully instrumented. Again, I'm after a proof of concept here. So the first set of animations I'm going to show you, again, will attempt to replicate the static load test. This is the applied load at the head of the pile. This will track settlement and shaft compression. I'm going to show you the calculated settlement at the head, toe, and the shaft compression. And again, here I'm going to be showing you the applied load, the actual load, and how they compare against the calculated ultimate geotechnical resistance. Now again, keep in mind this is a more complex analysis because for much of the upper part of this pile, which includes the entire constant diameter section and roughly half of the tapered section, there is negative shaft friction along this part of the pile. All right, so in that TZQW analysis, I first have to bring the negative shaft friction to zero before I can start in the positive shaft friction curve. So let's see the animations now. Again, a lot early on, it's all happening as shaft friction, negative shaft friction being reversed to positive shaft friction, the same as was observed in the Holman Island test piles. I finally have maxed out on shaft resistance, and now I'm turning down at a much steeper rate and mobilizing the rest of the toe resistance. All right, I started out with about 50% of the toe resistance mobilized. And there's the end of the simulation. So, what have we seen? First of all, we actually, at the head of the pile, we matched the observed results pretty darn well. Notice that we see less shaft compression. Before we had 10 millimeters, so now we got about, what, about 8 millimeters, a little bit less shaft. We see the results that are the same as we've observed in other deep foundation elements with residual loads. Again, the blue curve is the true resistance, and as we would expect, it has coalesced on the measured geotechnical ultimate resistance. We have a little bit of a difference here, and this is just due to the numerical approximation. The green curve is the measured resistance. And if we were relying on this, we would think we had about half the toe resistance than we really have. And to see how realistic this result is, let's compare it again to our instrumented load test piles. Again, the residual load distribution I assumed is a reasonable, simplistic approximation of the actual residual load. The measured load is again broadly similar to the measured load. Now I only assumed 50% of the toe resistance mobilized. In the instrumented piles at Kennedy Airport, almost 100% was mobilized. And here's the true load distribution. And again, here's my true load distribution. So again, considering the approximations that I made, the end results I think are really agree very, very well with the instrumented load test piles on pretty much identical monotube piles at Kennedy Airport. Notice a difference between the measured and the actual load distributions. Let me show you another simulation. Again, we want to see how the geotechnical resistance is mobilized as a function of pile head settlement. And again, we're going to see how the axial load distribution is mobilized. Now, I want to point out to you here that, of course, the total resistance, geotechnical resistance, has to start at 0. All right, after the pile is installed in the ground, there's no load on the head of the pile. So the total resistance at the head of the pile is, of course, 0. But what is different from the baseline no residual load case is that I'm starting off with a net negative shaft resistance of about 100 kilonewtons in this case. Because most of the shaft of the pile, and I showed you previously, well, I show you here, the entire constant diameter portion plus about half of the tapered segment has negative shaft friction. So the net negative shaft resistance is about a negative 100 kilonewtons, and the initial toe resistance, I assumed about 50% of the toe resistance was mobilized as about 100 kilonewtons. So although the total is 0, the two parts that go into it, the shaft is negative, the toe is positive, and of course they have to balance out to 0. So the difference we're going to see here is as the load is applied and settlement occurs, this toe resistance is not going to start from 0, it's going to start from an initial positive value, whereas the shaft resistance has to start from an initial negative value before it goes up. All right, because now as we load the pile, what happens, and we see this actually in this simulation, all of the early load that's applied to the pile is taken up by converting the negative shaft friction to positive shaft friction. That is from drag load to resistance. And this is identical to what I showed you for the Holman Island test piles in Norway that were done over 50 years ago. Very nice, they showed you that, in that case, they had to load the piles to geotechnical failure to convert all of the negative shaft friction from residual loads to positive shaft friction. So this is really the heart of what I've been trying to show you in this, one of the many things I've tried to show you in this presentation, is that when you have residual loads, as we do to varying extents in just about all types of deep foundation elements, when you apply load at the head of the deep foundation element, that load is going to be basically taken up in large part, if not completely, by first converting the negative shaft friction to positive shaft friction before any of that load ever reaches the toe. And because of that, you get a much, much stiffer response. And I'll show you that with some plots in a minute. So, okay, let's look at the animations now. Here we go, toe starting from an initial positive value, shaft from initial negative value. Everything being taken as shaft friction, converting negative to positive, until now we're starting to just about max out the shaft resistance, and any further resistance has got to come from the toe. Much softer response now because all additional resistance is coming from the toe. You see the shaft resistance stays maxed out. So at the end, we see that the actual load distribution is, as we would expect, the theoretical resistance curve, whereas the measured differs. We overestimate shaft friction, underestimate toe resistance, because the measured results don't reflect the fact that we had to overcome a deficit of about 100 kilonewtons of shaft resistance in this case. Well, let's now compare the analyses, no residual loads versus residual loads. This shows you the calculated head settlement at the pile versus the measured. The solid red curve is with residual loads, the dashed red curve is without. And clearly, when we include residual loads, we match the measured data better, and we see a much stiffer response. And this is exactly what I showed you earlier in this presentation when I showed you that the geotechnical benefit of residual loads is that since you've already pre-mobilized some of the toe resistance, the applied load now is largely taken up by converting negative shaft friction to positive shaft friction, which requires very little displacement, so you're going to get an overall stiffer response. So, you know, as Fellini said, the only thing negative about negative shaft friction is the name. It actually is quite beneficial. As I showed you, a driven pile is not only a tested pile, but a driven pile is a stiffer pile, and taper makes that even better. So the benefit of geotechnical benefit of residual loads, especially with driven piles, especially with driven tapered piles, is that they have a much stiffer response than you think, which is beneficial. And again, we could see how this shows you how the geotechnical resistance is mobilized as a function of settlement to head of the pile. We could see again that we get a much stiffer response considering residual loads versus not. And this is the shaft resistance. Without residual loads, we start at 0. With, we start at negative value. And again, the solid green curve is with residual loads. We see a stiffer response as load is applied. But of course, they all coalesce to the same curve, and they must. Okay, as I said to you, negative shaft friction, residual, whether from residual loads or global settlements, whatever, does not take away from the ultimate geotechnical resistance. It never does. And we see that. We see the two curves coalesce in the exact same curve as we would expect. And this just shows you how the toe resistance is mobilized. Again, without considering residual loads, we start at 0, but with residual loads, we start at a positive value. So that actually helps us because it takes a lot more settlement to mobilize toe resistance. So by starting with some of the toe resistance mobilized from residual loads, that helps us out with a much stiffer resistance. And here's a comparison of the elastic compression of the shaft. When we consider residual loads, we get much less shaft compression because the load does not have to go all the way down to the toe of the pile. Half the toe resistance was originally already mobilized. So all of these are positive results, right? Residual loads, considering residual loads is a positive outcome for the geotechnical purposes. So to sum things up, the preceding calculated results demonstrate that the TZQW methodology is a viable tool for analyzing the response of deep foundation elements to post-installation externally applied axial loading. The concentric cylinders elastic model that I use, when combined with state-of-knowledge site characterization outcomes from pisocone and seismic pisocone soundings, combined with an appropriate modulus degradation model such as the Fahey-Carter model, all in all is a viable approach for modeling the spring stiffnesses of the TZQW methodology. Note, however, that it is essential, emphasis on essential, to obtain site-specific shear wave velocity data, preferably from a seismic pisocone sounding, from which the site-specific values of the small strain shear modulus Gmax are calculated. And the reason this is so important is there is no shortage of empirical correlations for shear wave velocity based on any number of things, including those based on the QCFSQ-U2 data from pisocone and seismic pisocone soundings. The problem is all of these empirical correlations for shear wave velocity, which you need to calculate small strain shear modulus, are based on assumptions that the soil has no what we call structure or microstructure that comes from cementation and or aging. All right, all of these empirical correlations assume what we call a young, well-behaved soil with no microstructure. And let me show you why that's important using data from Kennedy Airport. Now, these are from a couple of seismic pisocone soundings that were made earlier in the 21st century. This was for a passenger terminal project in the central terminal area at Kennedy Airport. However, the owner of that project asked that I keep the specific terminal name confidential, and of course I will honor that. So this is from these pisocones were taken during the same time frame, not only both at Kennedy Airport, both from within the same overall terminal site. So they're from a relatively limited horizontal extent at Kennedy Airport. If I had to guess the distance between these, perhaps a few hundred feet, maybe 100 or 200 meters. So these were relatively closely spaced. And I will just call them seismic pisocone A and B. All right, A is green, B is dark red. Okay, and very, very similar. I mean, not only compared to each other, but to all the many cone soundings I've seen at Kennedy Airport. These are very similar. So this is the corrected tip resistance, and this is the friction ratio. So very, very similar. I mean, if anything, down here in the deeper Pleistocene stratum, we get a little bit of a kick, a little bit denser layer here in pisocone A, but for all intents and purposes, identical. Now, I want to focus on the lower portion down here for comparison. These are the measured and calculated shear wave velocities. Now, the measured data are shown with the red squares in both cases. The calculated, this is with an empirical calculation that I found. I've looked at several empirical correlations for shear wave velocity from CPT soundings, and I found this is the best one. But the calculated correlation I use, this is for the classic young, well-behaved soil with no cementation. Now, for pisocone A, the measured results and the calculated results really agree very well. I mean, I have to tell you, it doesn't get any better than this. So we have excellent agreement between measured and calculated for A. And what this tells us is that in the area where pisocone A was done, that portion of the terminal site, there was no, we would say that there was no microstructure for the within the Pleistocene stratum. But look at Pisocone B. The measured shear wave velocities, they agree with the calculated until we start to get into the lower part of the Pleistocene stratum, and we get much higher measured shear wave velocities, much greater deviation between the measured and the calculated. And again, the calculated assume no cementation. Okay, so we're focusing on this area down here, and we see that the bottom 12 meters or so of these soundings. You see these soundings went about 30 meters, so almost 100 feet. So they went almost completely through the upper glacial aquifer. So again, these two soundings were done within days of each other, within the same general terminal area at Kennedy Airport, within the central terminal area. So these two are fairly closely spaced. And again, I point out that if you look at the tip resistance, you would not expect to see this deviation in shear wave velocity between the two. If anything, Pisocone A has this little bit higher density layer down here. Again, this is Pisocone A. So although this is a layer a little bit higher density here, it still does not have any microstructure to it. All right. You come across here, these are the same scales in terms of depth. You don't see any evidence of this little bit denser layer in the shear wave velocities. I now want to compare the calculated shear, small strain shear moduli values, G max, for A and B. Again, based on the shear wave velocities. And I calculated G max using both the mean or average data as well as using the median results, and they're essentially identical in this case. So again, we see that in seismic Pisocone B that the measured small strain shear modulus is much greater than we would expect based on no aging. And we can see that with some other plots. This is, if you've not seen this plot before, this is just this log plot just shows you basically a normalized cone tip resistance. And this is a stiffness parameter. This is the small strain shear modulus. In this case, the author used G naught. This is what I've been calling G max versus the normalized tip resistance. So this just shows you a plot of tip resistance versus stiffness, if you will. And what this is saying is that for what we call ideal soils, that is young, uncemented, they typically fall within these two parameter limits. This parameter K star G definition is shown here. But when we have soils with microstructure, that is cementation, bonding, and aging, they're going to deviate off to the right here. And if we show these results from seismic Pisocone A and B at Kennedy Airport, we see that A, all the data fall within the range that we would consider to be ideal soils, not exhibiting any microstructure. Whereas for B, at that deeper depth, this is all from that deeper, that bottom 12 meters or so of the soundings, we see that we are definitely getting some results that go off into the area where indicating that there is some microstructure. Now, this is what we observe. Why do we observe this? If you know, I would love to know. I have discussed this. I first learned about these results over a decade ago when I first got these data, and I had the opportunity to discuss this with some experts in cone penetrometer work, and I've yet to have a good answer. I mean, I have studied the geology of Kennedy Airport for over 50 years. And based on everything I know about the geology of Kennedy Airport, I have some guesses as to why we're seeing these differences. But they're just speculation, and I don't like to get into just unsupported speculation in these presentations. But it does illustrate that, you know, we would not expect to see the effects of microstructure, but we clearly do. And by the way, this was not an outlier. I don't want you to say, well, this is just one seismic piece of cone. Maybe there was something with this cone. No, at this particular terminal site, I fortunately had access to several dozen piece of cone and seismic piece of cone soundings. And these results were replicated by other seismic piece of cones. So within this overall terminal site, there was a portion of the site where all the seismic piece of cones were like definitely no microstructure. But there was another portion of the site where there were several seismic piece of cones that all exhibited this evidence of microstructure, and all at the same depth, the lower portion of the Pleistocene bearing stratum. So really the important point here is that never assume things. Now I've worked at Kennedy Airport for over 50 years. I've been looking at cone penetrometer data since the late 1980s as part of my academic research. So I have seen, I don't know at this point, well over 100 CPT, SCPT, SCPTU soundings taken at Kennedy Airport, almost all of them within the so-called central terminal area. And the point I'm getting at is the subsurface conditions at Kennedy are very uniform in the scheme of things, even though it's a very large site, several kilometers, several miles in horizontal dimensions in both directions. Although the geology is very similar at the Kennedy Airport site, there's always surprises. So the moral of the story is, no matter how well you think you know a site, you always need to do some site-specific seismic piece of cone soundings, a representative number throughout the entire site, because nature is going to show you some surprises every now and then, as they did in this case here. And the specific importance is because this microstructure affects the small strain shear modulus, it is going to affect the load settlement behavior of deep foundation elements. And that's why I'm making such a big deal of this. It's not just some idle academic curiosity. These things affect the shear stiffness of the soil, which hopefully now you see will affect the load-bearing stiffness of a deep foundation element. So in any event, to continue on, the calculated results have showed you that the effects of, including the effects of residual loads from installation, can improve the accuracy of load settlement forecasting. Both the TZQW methodology in general and the concentric cylinders model in particular can be readily modified, and I've showed you this already, to include residual loads, although this has not been done historically. So in summary and conclusion of this phase 2 presentation module, it is clearly feasible to change design practice for deep foundation elements subjected to post-installation axial loading to focus primarily on the geotechnical serviceability limit state, that is, axial displacements, especially settlement, with due consideration of the structural ultimate limit state, simply by taking advantage of analytical methodologies and methods that already exist and have been well proven in other deep foundation applications. This conclusion supports the overarching thesis of this presentation, that deep foundation element design practice that is primarily based on the geotechnical serviceability limit state is not only logical and justified, but can be immediately implemented into routine practice with nominal effort simply by making use of knowledge that has been available in the public domain for decades. So I feel that I've basically proved what I said at the beginning, that we need to change what we're doing when it comes to the analysis and design of deep foundation elements for axial loading. We need to make this change. We've needed to make this change for a long time, and we can make this change, and it doesn't require any extraordinary effort. All the knowledge and information we have that is necessary to make that change is out there, and you could make this change today if you wanted, with this available information and using nothing more than generic spreadsheet software. So with that, I want to move on to the penultimate module of this presentation with some closing comments and observations. An important element of this presentation has been to illustrate that while changing the current state of practice for deep foundation elements subjected to axial loading, to focus first and foremost on the geotechnical serviceability limit state is an important goal. Equally important, to the point of being mission critical for achieving this goal, is improving the current state of practice that focuses on the geotechnical ultimate limit state. As I said earlier in this presentation, sometimes you need to be better at what you are doing before trying to do better than what you are doing. And this is certainly one of these times. And this is because the current state of practice will, of necessity and in consonance with good practice, continue to coexist with a changed state of practice based on the geotechnical serviceability limit state for some period of transition that will undoubtedly be years, as neither building and design codes nor professional opinions change overnight. In addition, even after this transition is completed, being able to forecast and measure the geotechnical ultimate limit state accurately and reliably will remain an essential mission-critical part of the geotechnical serviceability limit state design process. Thus, a high priority will be to revisit the various methodologies and methods that are currently used for forecasting the geotechnical ultimate limit state, and revise them as necessary to account for the effects of residual loads from deep foundation installation on the databases that were used and are used to develop or calibrate these resistance forecasting methodologies and methods. This is necessary as resistance forecasting methodologies and methods in their current versions tend to overestimate shaft resistance and underestimate toe resistance. This presentation has also produced some unintended insights that are relevant to several things. The geotechnical serviceability limit state, the geotechnical ultimate limit state, and what we now call the carbon footprint that has become an increasingly important consideration in the planning and design of all aspects of engineered construction, including foundations. And each of these three topics will be discussed on the following slides. So what I want to talk a little bit about are things that I didn't expect to come out of this investigation, but did. First of all, considering the geotechnical serviceability limit state, this presentation has demonstrated that the methodology used to install or construct a deep foundation element into or within the ground plays a very significant role in the geotechnical serviceability limit state of that deep foundation element by virtue of the relative significance of the residual loads due to installation. The most important aspect of residual loads is that they pre-mobilize a portion of the tow resistance, sometimes substantially. So in simple terms, the larger the residual loads as a percentage or fraction of the geotechnical ultimate limit state, the stiffer the deep foundation element response will be to post-installation externally applied axial compressive loading. As this post-installation load is taken up largely by shaft resistance, as I've illustrated both in theory as well as from case histories, essentially reversing negative shaft friction into positive shaft friction, which is an inherently much stiffer axial load bearing response compared to mobilizing tow resistance. Stated another way, the benefit of residual loads is that it basically pre-stresses tow resistance, which we know in general takes a lot of displacement to mobilize. So it pre-stresses that component, and it therefore shifts most of the loading to shaft friction, which we know takes relatively little displacement to mobilize. This fact naturally tends to favor deep foundation elements that inherently have relatively significant residual loads, such as traditional driven piles in general and driven tapered piles in particular, as experience indicates that driven tapered piles have relatively larger residual loads with significant mobilized tow resistances, in some cases approaching 100%, compared to comparable driven piles with a depth-wise constant perimeter, a fact that was illustrated earlier in this presentation. Right, and this is a curve that I've shown you a couple times. This came out of the Holmen Island, Norway test program in the late 1960s. And what we're showing here is two piles with identical embedment lengths, a constant diameter pile, and a pile that the lower half of the pile is tapered with a taper similar to a test pile. And again, we're showing you here the residual load as a function of depth. And we see a very significant difference. These two piles are basically the same for the upper half of the pile, the upper 8 meters, which in both cases was constant diameter. But for the lower half, which was tapered in one case and constant diameter in the other, in this lower half that is tapered, we see significantly larger residual loads. Even though this taper is very modest, this is only the taper of a typical timber pile that we see in the east coast of the United States. Now, considering next the geotechnical ultimate limit state, it has long been known that driven taper piles are very efficient at developing the geotechnical ultimate limit state. That was noted by the late Professor Ralph Peck almost 70 years ago. And again, this is a quote that I've shown you now a couple of times in this presentation. So as I've noted earlier, a novel way in which to visualize the axial compressive load-bearing efficiency of any deep foundation element is to calculate its compressive resistance efficiency, CRE. It's a dimensionless parameter that was defined several years ago in my research in one of my publications. And again, CRE basically says how much load can a deep foundation element deliver per unit volume of that deep foundation element. So as I've shown you earlier in this presentation, the CRE for driven piles is very sensitive to taper angle, and thus CRE is a useful metric for demonstrating and quantifying the geotechnical ultimate limit state efficiency of driven tapered piles. So this is a graphic that I've shown you previously, but now that we've talked about a few more things, perhaps you could get more out of it. Again, what I'm showing you here is the compressive resistance efficiency, CRE, which is essentially the axial compressive load bearing per unit volume of a deep foundation element, and I did non-dimensionalize it to the unit weight of water simply so that we don't have to worry about units. And in simple terms, the larger the value of CRE, the more efficient the deep foundation element is in terms of material usage in supporting axial compressive load. And this is showing you CRE versus pile taper angle, and this is based on my research of driven piles at Kennedy Airport. These were some constant diameter piles, just to give you kind of a baseline. And here we see the results for some timber piles. These are all southern yellow pine, which is the typical species used in the east coast of the United States. I'll also point out that the monotube F taper, which is the least of the three taper angles in the monotube pile line, has a very similar taper angle to timber piles. These are the monotube type J taper piles. For example, pile P5A that I talked about extensively in the Phase 2 module was a type J monotube. And the instrumented piles talked about by Felinius and colleagues at Kennedy Airport in the early 1990s were also type J. And these are the latest iteration of tapered piles in use at Kennedy Airport, the taper tube with an angle of 0.95 degrees, which is also the type Y taper angle of the monotube pile line. Right? F, J, and Y are the three taper angles of the former monotube pile line. So we see that even for a relatively modest amount of taper, again, this is only about 1 degree of angle, there's a very significant increase in compressive resistance efficiency. And this just demonstrates in hard numbers what Peck said in words, and that is that even a modest amount of taper in a driven pile can greatly increase its load-bearing capacity per unit volume. Now, because the CRE parameter reflects the relationship between deep foundation element volume and the geotechnical ultimate limit state, the CRE parameter also has the potential to be a useful metric for the third and final issue I want to discuss here, and that is carbon footprint, which is also related to deep foundation element volume. As you know, carbon footprint is simply the amount of carbon that some construction material requires in its manufacture and use. So it's clear from the definition of CRE that as the magnitude of CRE increases, there is a potential, not a guarantee, but a potential for the carbon footprint to decrease. This is because for a given magnitude of the geotechnical ultimate limit state, as CRE increases, the volume of deep foundation element material required to achieve that magnitude of geotechnical ultimate limit state decreases. So less material to support a given ultimate load may mean that there's a decrease in the carbon footprint of that deep foundation element. Now, of course, the specific type or types of material required and how you have to drive or otherwise insert or create that deep foundation element in the ground is going to impact its carbon footprint. All these things play a role in the carbon footprint calculation, but the trend is nevertheless clear that a deep foundation element with a higher compressive resistance efficiency requires less material to resist a given magnitude of axial load. This then suggests that driven taper piles develop a fresh look not only for their superior geotechnical serviceability limit state performance and geotechnical ultimate limit state efficiency, but for their potentially efficient carbon footprint as well. So I have always been partial to driven tapered piles just because I think they were a very interesting deep foundation alternative. And in this presentation, I am showing you that because of their residual load tendency, that driven tapered piles will tend to have a stiffer performance, so a superior serviceability limit state performance. They certainly have a superior ultimate limit state efficiency, and they have the potential to be have a lower carbon footprint as well. Well, to wrap things up, I just want to make some comments about some acknowledgments. I've been interested in deep foundations in general and driven tapered piles in particular since literally the first days of my professional employment that began in June of 1972. So I've been at this for over 50 years now and have never gotten tired of it. I still enjoy it very much, obviously, otherwise I would not have made this presentation. Now, in those over 5 decades, there have been many individuals and organizations in the years since then who have inspired me, influenced me, and assisted me, and in particular my research into deep foundation elements and related topics, such as site characterization using the cone penetrometer, and they have been noted and thanked in earlier publications and presentations. And again, it is important for me to emphasize that I have not received any financial compensation at all for any of the presentations, including this one that I've made relative to deep foundations, nor for any of my publications, whether a monograph or white papers that I've made about Kennedy Airport, deep foundations, tapered piles. While certainly individuals and organizations have provided data to me in terms of raw data from cone penetrometer soundings and boring logs, for example, as well as pile load test data, these data have been provided without any quid pro quo. So there has been no financial compensation or expectation of benefit from any of this work. And that's very important because a lot of people do question science and engineering publications these days as to whether or not some professional has been paid to write a positive review of something or some technology, whether it's a drug or a construction material or whatever. But there has been none of that financial influence with anything I've done related to deep foundations, including this presentation. I made this presentation simply because I've been involved in the deep foundations industry for over 50 years. I am a charter individual member of the Deep Foundations Institute, so I certainly have always believed in deep foundations, been interested in deep foundations. But there's just some things that I felt needed correcting, and that's the reason I made this presentation. Now, of specific relevance to this presentation, I want to acknowledge and give heartfelt thanks to Mr. Regis J. Colasanti, PE. I have collaborated with Regis now for over a decade on several topics. Originally, it had to do with subgrade modeling and models and map foundation analyses, but I have drawn on Mr. Colasanti's many decades of structural engineering expertise and experience in practice for his insights, discussion, and theoretical work, and in this case related to the theory of elasticity concentric cylinders model. Mr. Colasanti's original research with the concentric cylinders model has shown that application of this model can be extended to include the radial displacement and concomitant stress changes in the deep foundation element ground interface that occur if the deep foundation element is tapered as opposed to having a constant diameter. I have not, however, incorporated any of Mr. Colasanti's theoretical work into the calculated results of this presentation, simply because they have not advanced to the point where they are producing any usable results. But I have every intention to include his work in future developments related to the concentric cylinders model as part of a TZ QW method for deep foundation element analysis. So with that, I want to give a heartfelt thanks to any and all of you who have listened to this entire presentation. I know that it is my longest presentation by far. I knew that as I was preparing it. I've been working on this presentation on and off for the better part of the last 2 years. So I knew it was going to be a very substantial, lengthy effort. And for those of you who have listened to it in its entirety, I thank you. I hope that your patience has been rewarded by perhaps learning a few new things, or maybe learning new insights into things that you've known already. So with that, I want to say thank you again and close out this presentation.